What's up, YouTube? Okay, it usually doesn't capture that. Okay. Does anyone have any pressing questions about anything before we get started? Oh, I'll have a nice time. Do you all know graph theory? Okay, let's learn some graph theory. Yeah, not to worry. Whenever I finish these slides, which usually is not before dinner, usually it's like 45 minutes after dinner, right? I notice I speed up through the night because I'm getting less friction because you get tired and ask fewer questions. So I'm actually trying to figure out when I should be changing between the two lectures because it's not at 7:30. It's like at 8:45 or later, but I'm not exactly sure when it is. But I also noticed this with my data 505 down in Salem because I have Hendrick and Jameson slides and they have dinner breaks in them. And like we usually get to the dinner break at like 9 o'clock and then like finish all of the slides and what feels like good to me. So I don't know if that's me. Oh, sorry. No, I was going to introduce this. Okay. So we're going to introduce graphs. Um, um, Basically for no reason. I'm going to teach you about directed acyclic graphs. It's not part of this course. It's something I think you should know. Um, and then I'm going to teach you about trees. You've probably used trees before. Sometimes you do this with or without knowing them. The thing I wanted to do with trees is a general and very powerful tool called the B tree. The B tree is what implements most database applications. Um, they look complicated, so we're it's like backed off from that. That looks like it should be a class. But you should at least see a couple ways to use a tree in C. Under the assumption that the way C is using trees is how everyone else is using trees too. They just don't expose that to you, right? Um, then we're going to do hash or Merkle trees, and the hash and Merkle trees is the second half. So that's on the separate slides. I waffled so much on the corresponding assignment for this because I thought it might be interesting to ask you all to implement a Merkle tree because that would require you to make a sort of record data type data structure and compute a hash over a data structure you made. And like maybe that's like a cool thing to do, right? Like sort of round tripping your code. And one of the reason I stepped away from doing that is because the only way I could figure out how to explain the way I was going to recommend that you implement a Merkle tree is by basically teaching everything about heaps but not mentioning the term heap. And a heap is an independently interesting abstract data type. So I thought I'd spend the extra like 10 or 15 minutes going over heaps as a motivating example to explain Merkle trees. And then I can ask you to implement heaps in C, which is a much more general thing to do. Are those whiteboards like super in the way?
Yeah.
Yeah, let's do that now.
This one. Perfect. Then it's not my problem.
So you do know what trees are. Okay.
What?
Hot. Okay. Do you know about graph theory?
Yeah.
Yeah, that's good enough. Right. Within a blockchain block, there are four fields. There's the previous block, usually we say the hash of the previous block. There's the timestamp. There's the number that is only used once. And then there is the Merkle root. And what is the Merkle root? The Merkle root is a complex nested hierarchical hash of every transaction that goes into that block. It's called the Merkle root because the tree type of graph has something called a root. The Merkle tree has a Merkle root. So to get to a point where I feel like I'm not just hand waving and telling you that these things called trees are out there, I was going to procedurally step through graphs. But we're going to begin with this definition, which is the n-ary tree. A tree is a type of graph. What type of graph? We'll get there. What is a graph? When I say graph, I am referring to an ordered pair of a set of vertices and a set of edges. The edges are pairs of vertices. They may or may not be ordered pairs. If they are ordered pairs, we call it a directed graph, and if they are unordered pairs, we call it an undirected graph. Now, something I have historically not really loved about all of this stuff is that when I was learning all of these things, I didn't get a rigorous definition of what an ordered pair was. To me, it is natural in computing and computer science and mathematics and these other fields to think of everything as a set, but sets don't have order. And when I make a graph, I need to keep track of whether the vertices or edges come first, or maybe I don't, maybe I only store the edges, right? But I also need to keep track of, in the case of directed graphs, which direction the edge goes. To step through this, I'm going to use a little bit of mathematical notation, and we're also going to have a running example of the Amtrak Cascades line. So that's how I was going to teach this, and then when we're done with that, we'll understand more please. Okay. I think graph theory is accessible. I was going to pitch the program this year on teaching a class called Sets, Graphs, Automata, and I actually just took all the material from that class and put it in this class in various points. So now I don't have to teach that class. That's pretty cool. And now you can say, sets, graphs, and automata. Now, in fairness, 100% of the automata theory is going to be in that one lecture we're going to do next time. But it's an automata. It's not that hard. No one really understands them. So the great thing is it doesn't really matter how long you study them. You understand them about as well as anyone else. So I'm going to use the running example of Amtrak. And in the olden days, I could point and you could see where Amtrak was, but I think it's in that direction. But it's a couple blocks, right? Yeah. So I think we're all web developers here, at least some of us are. I just want to point out that this is an embedded GIF with a border radius on it. This is the first time I've ever wanted to use a 100% border radius. And it just looks great, right? There's an animation. I didn't make this thing. But I think if I open this in a new tab, by golly, it's a square, right? I got rid of all that stuff. Look at that. See, that's gone. So anyways, I wanted to shout out my border radius. I thought it looked pretty cool. Here's the definition of a graph. Okay. The graph is an ordered pair. It's two things. They're in a fixed order. We can think of an ordered pair as a sequence of length 2, but I haven't come up with a way to define sequences. I am accepting as a given set theory, and I'm doing specifically ZFC set theory, which is the set theory that the mathematicians tend to use, which stands for Zermelo-Fraenkel set theory with the axiom of choice. The reason I use that one is it's the only one I know and I've heard it's consistent. I don't really want to figure out whether I use other ones. It doesn't seem a big deal whether you use the axiom of choice or not in most of the stuff I do, because I tend to be dealing with finite numbers, so I don't have to worry about it too much. And the axiom of choice is this whole thing, right? But it does actually come up in some computer science proofs at various points in time. So anyways, an ordered pair can be thought of as sequence of length 2, but I'm only assuming set theory, so I don't actually have sequences. Now, I bamboozled all of you into implementing either a linked list or an array list last week, which means you know how to implement ordered pairs, probably more than you want to know how to do them, right? But just because we can do it with electrical engineering doesn't mean we can do it with mathematics or computer science, so we should take some care to actually make sure we know how to implement this thing. The real critical thing is that given a set, I can't index it. I was writing some scripts with some mathematicians the other day, and we needed to get the first element of a set for one of our proofs, and it's well, that proof's dead. You can't do that. There's no way to ask for the first element of a set. You can ask for an element of a set, right? That's allowed. Python does correctly prevent me from looking at the index of an element in a set. It does some other things that I think are not great. Python sets are definitely not the same thing as mathematical sets, and I would really like them to be, because there's things I would like to do with Python sets that I can't do with them, and one of those things is put sets inside of each other, right? Oh, right. Okay. I was on a bit of a web design kick. We all love the canvas element, right? Oh, click, it draws. Yeah, right. Like, this is fun. Um, what I realized I should have done, right? I should have changed that background to be the same color as my slide background, right? But you know, um, so why is the ordering of pairs important? I always think of the ordered pairs because the first time I heard the term ordered pair was very specifically in a mathematical context, and since it was in math class in middle school, right? And there we used ordered pairs to differentiate locations in a two-dimensional plane. Um, and this should be interesting to us because we probably think about planes a lot, right? Anytime you use a multiple dimensional array, this is what you're dealing with. There's so many other things. I don't know what you all are learning in Data 505, but I drew out a projection of vision space for computer vision into a one-dimensional vector, so a 2D to 1D dimensionality reduction the other day. So we're always sort of dealing with these things, right? We can imagine this as a computer vision problem or anything else, right? Now, if I have an ordered pair, 0.5, 1.5, if that's a set that doesn't correspond to a location, so I'm losing information, I'm not accomplishing my goals, right? And in this case, because in my middle school class, I learned, I think like you have to run before you can jump, is how they described this. I did a horizontal displacement of 0.5 units and a vertical displacement of positive 1.5 units. And that gave me that little red dot. But most importantly, this gave me a unique location. And that unique location with the ordered pairs also corresponds to a unique edge or a unique graph or some other unique thing. If I change the orders of all my edges on my graph, perhaps it is some different graph, right? And so most importantly, because that's an ordered pair, we did not also get this location over here, which is horizontal displacement of 1.5 and a vertical displacement of 0.5 from the origin at 0, 0, right? And so when I think of ordered pairs, I'm always thinking of dimensionality, I'm thinking of location, I'm thinking of avoiding information loss. These are sort of all of the ideas that are concurrently swimming around in my brain. And in order to solve that problem, I stepped through this somewhat lengthy example. Importantly, you cannot do this in Python. Well, can I do this in... Are there sets in JavaScript? Let's try it. How do I get to the log? There it is. Okay, so if I say, is that a set?
You don't have to instantiate.
Okay. It's one of these? Okay. Yeah, I guess I don't know what I would provide to a set. Okay, that's interesting. Okay. And then, okay, that's cool, right? Because if I did, it would give me back something. Okay. I don't like that it has square brackets, and I also don't like how small it is. Wait, do I have node? No. Okay. There are a variety of programming languages, they all treat sets differently, and that's not a good sign, right? Um, this is consistent with my understanding of mathematical sets, which is you're allowed to put sets into each other. Oh, I didn't even check to see if I can put a set inside a JavaScript set. Right? Surely they'll let me do that. Okay. So we have, we'll use S0 equals new set 1, 2, 3. And then we will create S1, which will be new set of, are they typed? Can I put a 1 and a set in the same set? Yeah, is this just a typo?
Yeah.
Okay, so yeah, there we go. That's fine. Um, Okay, so we can put sets inside themselves in JavaScript, which is actually extremely useful to us. So we're going to save this tab and we're going to wish. Oh, went away. See, come back. Come back, inspect. I just want node. Quick. No. Okay. I'll step through this example and then I'll attempt to write one in JavaScript on the first try. And then I'll try and figure out. Oh, this is the new computer. That's why it doesn't have node on it. Right. Okay. Because I'm convinced. Yeah, I wrote node in this class in like week 3 or 4. I opened up node and was writing something. Um, maybe not. Maybe that was my class. There was a node application, like just on my taskbar on Windows that I opened at some point, and I don't know what it does, so I'm scared to close it, right? I can't tell if it's like critical infrastructure. Like, what did I write in there? Why is it running? And you go look at it, and it's just like, yeah, I don't know. Anyways, okay. So we're making ordered pairs, and we're going to make ordered pairs out of sets, and we're going to make them on this slide, and then we're going to make them in JavaScript. Okay. Say I have A and B, which stand for I don't know. They stand for A and B. Okay. And I need to only using sets denote that one of them comes before the other. So I do this, I create a set of cardinality 2, and I call this the outer set. This outer set is going to contain 2 elements, and both of those elements are themselves going to be sets. One of the elements, which is not the first element, but we will think of it as the first element, is the set that contains A, and only A. The second element is the set that contains A and B. So, what does this mean? This means if you are in both sets, you are the first or initial or leading element. And if you are in one set but not both, it means you're the second element. So I can include ordering information using unordered elements using this technique, right? And now let's write that in JavaScript and see if we can get it to work. Okay, so. Oh yeah, it does get bigger. Okay. So I have my elements. Create A and B. Oh, is that not allowed? Yeah.
So just to be clear, if you wanted to each element is itself, we should be.
We should think of it that way, and we should also think that we can create ordered collections from unordered collections recursively.
And can you define collections?
I think of collection as sort of the higher level way of describing sort of a lot of data structures, but also mathematical objects that just contain data or information, but not necessarily a specific type of data or information. So sets contain these things called elements. But like so does an array. And maybe so does a sequence, right? I often think of sequences as necessarily containing numbers, but there's not really anything compelling me to do that. If I happen to only have an unordered collection, which is a set, I can create an ordering out of it. And I create that using recursion. And recursion is one of our like high-level learning goals for the semester. So just seeing it up front. Okay. So I was going to create a set called the outer set. Can I add elements to a set once I create a set? Is it like set insert or something? Or okay. So we will let outer equals new set, and I'm going to start with an empty set. Then I'm going to create, we'll call it the initial element. Do I need to do that? No, I'm going to do outer.add new set, and I'm only going to put A in this set, and I probably have to put it inside an array. And then I'm going to add another set, which is the set A and B. Oh, did that? I didn't update her, yeah.
different depending on methods, and there could be one. Main thing.
It's a function. Wait, that's not how you write for loops in JavaScript, right? It's this notation? Is that how you write a for each? This is I definitely wrote Python there. Oh, that's not what I expected. Console.log's working, right? Oh, I'm not in Chrome. Should I switch to Chrome? So, anyways, our takeaway is that you can put a set that contains one element and a set that contains two elements in the same set. And I'm going to use set theory notation for this. And if you want to hack around on this and figure out what we should be doing, just let me know. Oh, yes, I should demonstrate. It's always important to make fun of Python when you get the chance because it does a lot of things well. So when it does something poorly, we really want to jump on it. Why did I not do multiple assigning? You can't even attempt this in Python.
It, um, you can also provide values page. You can also there you go, kind of closer. You can do e likely e dot values inside of that. I'll leave that on.
The entries are. That's good. That's what we wanted. Right, so I have a set that contains the set A and the set AB. That was what we wanted. There's just no grateful way to print it, I guess, right? But like it's trying to show me something, right? Yeah.
No, I thought it was more. This might be pretty close.
That's pretty close, right? Because the only things I was going to use are intersection union at set difference, at which set difference is sometimes hard, because you would not naturally implement that in a programming language.
Even the metric.
That's pretty recent. I don't use anything that was implemented in my lifetime, as you've all learned from watching me teach. Python getting in on a technicality because it's not my fault that version 3 is the new one, right? You know, this 2 is just no longer supported, it has security. So here's the bad thing Python does, which you can't even put sets and sets in Python. And why is that? Because what is that sound coming from? Why are we hearing the lecture? I'm losing my mind. Okay. If we close the door, does it help? And thank you. I suspect it's coming through this. That's really loud.
We'll do it. See. Yeah. Yeah. You can do that. Person. Oh, so it's a light seems like that's fine. The video that's way louder.
It's also extremely loud in that room. Like, yeah, yeah. I was like, "Can we turn it down?" And everyone's like, "I was like, okay, but then why did you wait for me?" It looked like a no rules angle. But like, who shows up when there's no professor? First of all, okay. Um, here's my formal definition of an order. An ordered pair is a set of two elements, a set containing the head element of the pair and a set containing both elements of the pair. I sort of you don't want to say first because it might be zero indexed. So what do you call the element that is the one you see before the other ones, right? I've taken to using head and tail with linked lists to refer to the initial and ultimate, or very last element. And then if I think of an ordered pair as just a linked list of length 2, then I get to use head and tail, which are sort of convenient terms, right? And in another version of this class I taught that I think is probably going away forever, the linked list motivating example is you implement the game Snake. And so the head is actually the head and the tail is actually the tail, right? And that's actually probably the best reason to teach Snake is that it's like literally a snake. And then I had one student refer to every linked list node as a snakement, like segment and snakement combined. So that's when we got in trouble. Okay, we exceeded the fun limit. Using set operations, this is how we can extract the head. It's not too complicated, right? You have a set, and I tell you that this set is an ordered pair. And you say, no problem, I can extract the head element as follows. I will take the intersection over all of the elements of this set. And by applying intersection to all of the elements of the set, you will get back only the element that is in all of the sets, and the element that is in all of the sets is the head element. By definition, that's what we constructed. There's different ways to describe this. I find this like big intersection, like a summation style intersection, the nicest way. But there are other ways as well. You can say for all of the pairs in the ordered pair, or no, for all of the sets in the ordered pair, X is an element of the set. And I didn't really know what to put here instead of Y, so I don't know that Y is the best letter, but that's what I did. The tail is incrementally more complicated, but that's okay. It's not really a huge deal. Presumably you're going to look for the head first, and maybe like once you have the head, you're going to know what the tail is by construction. But this is a little bit long, and I'm going to say it out loud. The tail is the sole element. So there's one such element that it can't be the tail. The tail is an element of the union, so not the intersection. The head is the element of the intersection. But the union, but all of the elements of the ordered pair are elements of the union, right? Because the union contains the set A and the set AB, and so when I take the unit of all of those, we get AB back, right? We're just taking the larger of the two sets, right? But it is not an element of the intersection. So all I have to do is take the union and subtract the intersection. Now I'm cheating a little bit here, because on this slide, I said element of the intersection, right? So I have to be careful that this whole thing, that's all referring to a set, and that's what I am taking the element of, right? So I don't actually know how you view precedence here, but importantly, I'm not taking the set minus of this x. I'm taking the set minus of this union. So I take the union over all my sets, it gives me AB. I take the difference of my, or the intersection of my sets, that gives me A. I take AB set minus A, and that gives me back B. And I express that here the same way, but without using big union and big intersection. And that's that. Yes.
I don't get what you're intersecting and what you're doing a union on. Isn't a subset of this thing? Of the larger set?
It's all of the sets in the pair.
Occasional?
The pair is a set of sets. So I'm taking the intersection over the inner sets.
The intersects that
The set of cardinality 1 that contains the head, and the set of cardinality 2 that contains the head and tail.
okay, you're saying each element can have any number of elements inside its set.
Yes, in general, sets can be of any size. Once I sort of pass the type check that I have an ordered pair, by construction, an ordered pair is an outer set of 2 inner sets. One of the inner sets contains 1 element, and one contains 2 elements. And those are these elements.
Okay.
Right. So I'm taking the intersection over all of the elements of this set. All of the elements of this set are A and AB.
But like specifically this, not just any set, but like 2 sets inside of it.
Yeah, this would only work for the ordered pair as we defined it. Yes. So yeah, intersection of all elements of P, if P is an ordered pair, I think is probably missing. Okay. Oh, excuse me. Okay, so do you have to actually spend class time rigorously defining ordered pairs? No, but I think you should. So thank you for coming along. You all now can build ordered pairs out of sets. So don't come crying to me if someone gives you a bunch of sets and tells you to make an ordered pair and you can't do it. I taught you. Okay, so now that we have ordered pairs, we can define a graph. A graph is an ordered pair G. And there's an ordered pair over 2 elements, the set of vertices, vertices, I don't know. I'm going to call them nodes, vertexes, and vertices interchangeably and just do your best, okay? I tried very hard to say specifically either vertices or nodes there, and I still got the third one, vertexes. So that says vertices, V, and edges. Okay, so a graph is an ordered pair, VE, and we can think of that as a set of the set of V and the set V and E. I'm going to switch to the running example here to motivate what vertices are. Vertices are the stops on a train. They're the nodes we connect. On Facebook, nodes tend to be people. In a linked list, nodes tend to be data elements. They can be sort of whatever you like. But in Amtrak, I'm going to think of them as stations or stops. Now, I'm sure there are other ways to represent Amtrak as a graph, right? I'm just going to use the example of train routes. Excuse me. There's an unusually high amount of carbon dioxide in my sparkling water tonight, which is causing me to begin to levitate. Okay, so on Amtrak, I never know how people refer to stations. I usually think I hear people say, I'm taking Amtrak to Seattle, not I'm taking Amtrak to King Street Station. And I think that's because all of the stations in the United States are named either Union or Central, so you can't actually refer to them by name. But Seattle has the uncommon cool factor of having a King Street Station. And then somehow New York City has both Penn Station and Grand Central Station, which seems like cheating. Because I think they also have 2 teams and a bunch of athletic conferences and stuff, so... Yeah, but do people get rights or do cities, right? because we think we're the same thing as Los Angeles and no one lives here. Right. So if we're by population, right, Portland contains roughly 700,000 people, and Los Angeles County contains 10 million people, right? So they should have 15 NBA teams. Okay. The edges, I think of the edges, I'm going to say a word, and it's not on the slides that much. Atomic. These are the atomic connections. These are the connections where you can go from one station to another without stopping. Why do we make it atomic? It makes all of the assumptions later easier, right? So, for example, there is not a Portland to Salem edge on Amtrak Cascades. It goes through this place that I hear actually exists, but no one has ever seen or heard of, called Oregon City. Have any of you ever seen or heard of Oregon City? Likely story. That sounds like what someone that wants me to believe Oregon City exists would say, right? So I'm a little suspicious. So I think in this classroom, at least, we can all agree that we know Oregon City doesn't exist, right? But it not existing doesn't prevent it from being a vertex, right? Many vertexes don't exist. And so there is no Portland to Salem edge, but there is a Portland to Oregon City edge, and there is an Oregon City to Salem edge. And when you put those two edges together, you can get to the state capitol and do whatever it is you do there. Some groups were there asking for more funds for trails today, right? So that might be something to do in the state capitol. I was getting my car repaired because it did not make it all the way to Salem intact, but it's fine now, probably. So what is an Amtrak? An Amtrak is an ordered pair. Don't tell Amtrak I said this. They might have a sense of self. But I think of Amtrak as an ordered pair, and it is an ordered pair of stations for train stations used by Amtrak passengers. And it is, the edges are the trains which convey Amtrak passengers between stations. Now, I'm very carefully saying trains because there is a Portland to Salem edge on Amtrak bus. And that's too complicated. So we're just saying buses don't exist. Has anyone in here ever seen a bus? Exactly. No, you haven't, right? So we love simplifying assumptions here in this class. And there's no Oregon City and there's no buses, right? Okay. So here are some of the edges. We're going to make an additional simplifying assumption, and we're going to assume that there are only three states in the United States, and those states are British Columbia, Washington, and Oregon, right? And probably some people would prefer that to be true, but we're just going to assume it, okay? And since we're going to assume that, we're also going to assume that the only Amtrak route is the Amtrak Cascades, which is operated jointly by the Departments of Transportation of Washington, Oregon, and British Columbia. Fun fact, this means that a train operated by a province in two states crosses an international border without involvement of either federal government, which violates the constitutions of both countries. And I've been on this train, which means that constitutions don't exist, right? Okay, so I think we can all agree. All right, okay, so we're going to consider the Amtrak Cascades route, and here are some stations on the Amtrak Cascades route. And look, it's not my fault. It doesn't make sense. They shouldn't have. There's like someone before the Supreme Court right now being like, look, have you heard of Amtrak Cascade? Anyways, these are the stations on the Amtrak Cascades. I think there's 14 of them, but this looks like 15. So maybe there's 15 of them. Something really fun you can do. Any of you from Vancouver? Oh, you're from British Columbia?
There's another video.
Yeah, right. Isn't that fun? So this is we're not going to do it today, but this is a fun data set to cause namespace collisions, right? Because if you're like, oh, let's clean this data, we'll get rid of the second word. Oh no, there's two Vancouvers. You can permanently go north on Amtrak Cascades because there's a loop, right? So anyways, yeah, there's two Vancouvers, and I always like to, I have a student from Vancouver, Washington, who I like to refer to as Canadian, which is really popular with everyone else. So anyways, here's our stations. we all know and love Professor Heather Kadada Smalley, so we've got Albany on there. We all know and love Damian Lil, the person that played for the Trailblazers. Is Carmelo Anthony currently playing for the Trailblazers? Oh, good for him. So he was one of the Denver Nuggets players. So, Salem, that's where the witch trials were. Bellingham, that's Budget Canada. Centralia is in the middle, right? And then Tacoma is where the airport is. That's Seattle's airport. So we were probably familiar with all of these. And there's some fake places on here too, like Oregon City, which doesn't exist, right? So these are all of the stations on the Amtrak Cascades, and that's still a little bit too much. But these are just examples of vertices. For our running example, I'm going to simplify this. I'm going to simplify it to the Portland to Seattle 6X daily trains. To my knowledge, outside of the East Coast megalopolis, there is only one profitable mass transit rail line in the United States, and it is the Portland to Seattle 6X daily. This is a revenue generating route for Amtrak, right? So take that, people that don't love public transportation. This is so public, we're not sure if it's owned and operated by the state or the federal government, and everyone's afraid to ask, right? And so there's 8 such stops. I have them in no particular order here. Why is that? Because that is a set of vertices. And because it is a set, it is in no particular order. So it might be reasonable to us to think, either Seattle or Portland should be the first thing in this set because this is a bunch of things from Seattle to Portland. No, the first thing is Centralia because it's alphabetically first, and I just sorted this arbitrarily, right? And the last one is Vancouver, not Vancouver, because we got to keep our Vancouvers straightened out here. So this is our running example, and I think this is just small enough and just intuitive enough we can get a sense for it. So perhaps you can all imagine where Tacoma is on this route, or where Vancouver is on this route. Edges are non-trivial, and they are specifically non-trivial in the following way. Sometimes they are directed, and sometimes they are not. I've been playing a little bit fast and loose with Amtrak because some of you may have realized you can take a train from Portland to Seattle or from Seattle to Portland, but it can't be the same train because trains go in one direction, right? Now, they could turn the train around, right? I know you're thinking, Calvin, they can turn the train around. No, they can't because they change the number when they turn it around. So it's a different train. It's a different platonic ideal of a train, right? At this point in time, I would like to reveal, I know all of you love that every single lecture has been about a 6-letter topic. Both Amtrak and trains are 6 letters long. I wanted to make sure you all knew that. Okay. So we have a set of elements. These are pairs, and if they are an undirected pair, they are a set of cardinality 2. They're just the 2 things that are connected. And if we are on a directed graph, then they are ordered pairs, and we know how to define ordered pairs, so we don't have to worry about this. What this means is that directed graphs and undirected graphs actually have wildly different type. One of them is a set of elements and a set of sets of elements, and that is an undirected graph. A directed graph is a set of elements, those are the vertices, and a set of sets of elements, because the ordered pairs are sets of elements, and so a set of ordered pairs is a set of sets. And so a graph is a set of sets. And that's recursion. Let's do a little bit of directionality. Some of you, this term, have been bamboozled by most likely me into either curling or W getting information off the internet. And you've probably noticed that you can't just use that to post files directly to the internet by specifying the URL to curl. That's because curl is a directed edge. It goes from the internet to your device, and it goes through a namespace server and all of these things. So the internet, I really think strongly as only having outgoing edges. It's very difficult to get an incoming edge to the internet. Now, at various points in time in this class, and probably in some of others, I've tried to get you to post things on the internet to make sure you know how to do that, right? And so purely because I'm preparing for this class, I make sure I post to Twitter, LinkedIn, Instagram, Blue Sky, and TikTok several times a day, right? Just to be a better teacher, right? And so there are, in fact, ways to get things onto the internet, but usually they're through mediated services and so on. So I think of the internet as something that is directed. I really think of pointers as directed. A pointer in C is how to find a destination. It says, if you go here, you will find something at this location. But there is nothing about that location where you go often on the heap, but perhaps on the stack, that tells you how you got there, right? When I get to some location in memory, there's not like a nice little travel guide that lists every single pointer that is incident on that location. And this is even more complicated with arrays because arrays are offset from a pointer, right? So if I go to the location array 7 in memory, there's no way of knowing what pointer sent me there, right? Pointers are one directional. We cannot follow them back. And one way to view this is that if I do 2 asterisks, that does not invert the operation, right? We can situationally use the ampersand to find the location of something, but that's just creating a pointer, right? That's not creating something in the heap or stack or anything. So oftentimes when I am using graph theory, I am using graph theory because I am thinking about how programs work. And when I think about how programs work, almost universally, the edges are directed. I can think of a function call as a directed edge. I can think of variable assignment as a directed edge. Some of us are R programmers, so you can say X arrow 7. That is a directed assignment, right? And so directionality is important, and it comes up a lot. I'm going to break my own rule, and I'm going to order my vertices north to south, and I'm going to do that as a matter of convenience. We're still going to understand that they're a set, and we're now going to say that, well, actually, the way we're ordering these is we're beginning to approach the notion of how we're going to define edges. So, what is an edge? In this north to south ordered collection, we can think of this as a sequence. We noticed that Seattle and Tukwila are adjacent, which was shocking to me. I was sure that there was an atomic connection between Seattle and Tacoma, but I was also sure there was an atomic connection between Portland and Salem. Right? Both of these shocked me. But there's all these imaginary made-up cities like Tukwila that allegedly exist, right? And so every time that 2 edges or 2 nodes or vertexes are adjacent, that means there's a corresponding edge. And if they're not adjacent, there is not a corresponding edge. So there is a Centralio to Kelso Longview edge. Those are the edges that occur immediately north of Vancouver, Washington. But there is not a Seattle-Tacoma edge, right? So, given 8 vertices, that means we have 7 edges. And there's a variety of ways to express these. Here's one such way. There's a Seattle to Tukwila, and these are ordered north-south. Now, these should not be ordered north-south. Why? Because these are the edges, and the edges are a set, and sets are not ordered. So this shouldn't be ordered, and there is a clear ordering here. We could argue like maybe this is what it looks like to be disordered, right? But I do want to point out there is nothing about this graph that is causing any of this to have to be ordered. Just a little note on notation. I used tuple notation, and one of the niceties of tuple notation is it's sort of ambiguously directed, right? When we look at this, I don't think it strongly implies that the Seattle to Tukwila edge is directed or not, which means that I can refer to this when I'm talking about a directed or undirected graph. And then I did maintain geographic ordering, which I'm not particularly proud of. We are coming up on our exercise, and you all love JSON, right? I really like JSON. It seems people often seem to think I'm kidding when I say I like JSON, but it is a very, very precise way of specifying ideas. Anyways, when I was trying to think about what's the best way to make a bunch of helpless students squirm, I thought JSON, right? I can ask you to express graphs in JSON. And in hindsight, this is the indicator that JavaScript was going to work the whole time, because I knew I could write graphs in JSON. I think of Python as supporting JSON too, but like, does it really support JSON? Or is it just like, that's a string? And you're like, it's supposed to be JSON, right? You are an object-oriented language, figure it out, right? So this is not JSON, this is JSON-like. But here is an expression of the Amtrak Cascades line. JSON-like. Where are some places I took liberties? I use variable definitions to avoid repeating elements, right? But we take, and I'm still using curly brackets to represent not ordered, right, for graph. So graph is equal to a pair. What is it that's paired? It is the pair of V, and this is the enumeration of vertices. And it is a pair of the pair V and E, E being the enumeration of edges. And so this is one way I can express, basically rhetorically, the idea of what a graph is. And now it is time for an exercise. We all love exercises, right? Like 4 people on the like feedback survey said like, hey, you should give us exercises during class. And I was like, should I though? Right. So anyways, this is for you, whoever voted for that. Amtrak recently added lines, including the Hiawatha, with service from Milwaukee to the world's greatest city, Chicago. Now, I don't know who broke into my slides and referred to Chicago as the world's greatest city, but I am willing to defend that claim with my life. Okay, let's just read about Chicago. What do you say? Right. From the grandeur of Grants Park's Buckingham Fountain to iconic museums and skyscrapers, see for yourself why Chicago was once dubbed Harry on the Prairie. Engage in retail therapy on the Magnificent Mile or root for the home team within the friendly confines of the famed Wrigley Field. Bears, Cubs, Sox, Bulls. That's what I say. Okay, so it's time for an exercise, and the exercise is I should do a partial land acknowledgement. The Hiawatha is the name or alleged name of a chief or elected representative of the organization I call the Iroquois Nation. The Iroquois Nation is the French name of that. In the Iroquois' own language, and my understanding is they're based in upstate New York, or what is now referred to as upstate New York. I believe it is the Longhouse people, and it starts Hudo something. I am not my best at maintaining names in other languages. And we should be aware of and acknowledge Hiawatha. When I was making these slides, I took actual great care not to make any references to the Amtrak line Empire Builder, which is not, I think, an appropriate name for a line. And so I did partially select the Hiawatha line for that reason. I don't know that this name was identified in collaboration with the indigenous nation, but I thought it was a nice thing. Okay, so here's the exercise. There is a route described here, and there is a JSON tester described here. Wait, why can I not open that? What? Does my browser not work? Look at that. I can't mouse over it. Oh, it's too low on the screen, probably? That's so interesting. Oh, you can get it at the very top. Okay, that's terrible. Wait, can I? There we go. Okay, problem solved. Just zoom out to 30%. I am a web designer. Okay. All right. So here's the description of the Hiawatha train. And here is a JSON formatter. You are under no obligation to try and get this to actually compliant JSON, right? But if you want to do that, you can do that. And so get this working. I'm going to go get some more water, and then I'm going to ask you all how you're doing. You're welcome to work in groups. I don't think this is too complicated or anything, but it's a good use of web scraping, basically. I was going to give a timer. Okay. Let's change.
lives.
You're welcome to do so. I did that as a convenience for me. Seems enough. Oh, hold on. What's this? I'm installing Node and it's using SHA-256 some? Hmm. Interesting. Far be it from me to claim I've taught you something useful, but yeah. I assumed you would need 7 minutes, which is a number of stops plus one. Is there only five? Two in Milwaukee, one in Chicago, two in between? It's plus one and one indexed. I don't know. Okay. Node. Okay, so we say the vertices are checked the map.
Um,
Sometimes you ask those leading questions.
well, there's another one that is with this next reference.
What? Oh, these should be all caps, huh? You can use double or single quotes in JavaScript. Please don't make me change it. But they're used for different things. Ooh, I'm not going to finish on time. Okay, new sets. Yeah, we had 7 minutes. Okay, I'm gonna try it. I'm gonna try and make it in JavaScript. If I export a set of sets in JavaScript, there's a way to just write that in JSON, right, and see what we get. Probably. No, I do love JavaScript.
But
Wait, oh no, this also goes in a set. Is there a graceful way to do this? Well, that's what I was trying to avoid. Here, we'll just do one. Or no, we'll do 2 edges. What's the next edge?
base.
Yeah, they're just ordered. Right. Glen to SVT, new set. Ah, no, set's lowercase. Wow, the punctuation is wrecking me, right? So to start this, I have to write lowercase new, camel case set, regular paren, boxy paren, either single or double quote. I still haven't figured out. And then I have to write all caps, and they're all 3 letters, new set, and all of the 3-letter abbreviations. Okay. Then I have to type. Okay. This is the type. This is what we want on monkey type. This is what I want to be tested doing, right? This is the meaning of my life. Okay. And then G is a new set of the new set of V. Nope, has to be in brackets. V and the new set. I suspect whatever you tell me to do in JSON is what I should do, but I don't have an intuitive sense for what that should be. Ah, how close was I? Let's see. Ah, there we go. Okay, I didn't get all the way there, but okay. So the question I was going to ask you, right, is like now that you're done, how many of you thought about whether you're going to implement this as directed or undirected, right? And so to me, the Hiawatha route is undirected. And why does it feel undirected to me? Because I think I can take the train from Chicago to Milwaukee and Milwaukee to Chicago, right? But if I go to, I don't really want to go buy Amtrak tickets right now, but well, no, I do want to be buying Amtrak tickets right now, but right. If I look at, for example, train status or something, yeah, let's go to Chicago to Milwaukee. Let's leave right now and come back in a while. Okay. Let's see. I am a child. Let's see if I pay less. Ooh, I want to be an infant. Okay. Submit. Ah, dang it. Okay. Let's see. I have a no, both of my cats are in this age range. Okay. I saw a video on TikTok of someone who bought their cat a plane ticket and was like, she likes her own seat. I was like, she's a cat. She likes whatever you tell her. Like they're not that opinionated. Okay. Yeah, but you can like trick them. Like we're smarter than they are. I've been bamboozled. So I think if I look at an individual train, such as the 329 or 331, a train is directional. And by train, I mean an Amtrak route cross number. Okay? So these things are directed. But let's roll the tape back. Do we have a course stenographer in here? Does someone okay, what is it? Oh,
You do.
it's YouTube. Okay. The Hiawatha line. Hiawatha route. The route is described here. Contains 5 stations. None of these imply directionality. So, your edges should have been unordered. They should have been sets of cardinality too, in my opinion. Otherwise, well, okay, they could have been directed, but then they should have gone in both directions. Just, just saying. Okay. Well, you all know graph theory. I sure hope there's not a bunch more graph theory right after this. Oh no, it's more graph theory. I hate it when this happens. That's not true. I love graph theory. Have you all heard of directed acyclic graphs before? Okay, cool. What context do you use them in?
I'm trying to think, because there's like certain graphs that are used under the hood for something, and what's the graph that's used to parse languages?
Abstract syntax trees.
Yeah.
Yeah. Yeah, I almost had an AST example in the slides today, and I was like, no one's going to know what that is. So there you go. But they're used in compilers all the time. DAGs are also package managers. This is package management. And then I don't know if any of you do like cluster computing, cloud stuff. So all the cloud stuff is now on Spark, and Spark describes jobs as directed acyclic graphs. So these things are all over the place. I'll give a few more examples as we go through. Do you want to break 9 minutes early for dinner and then do DAGs when we come back? Or do you want to go? Because this is kind of early for dinner because we're going to have a big block when we get back. But we're also at a good stopping place. I'm just going to talk for 8 minutes and then we're going to beat everyone else out there. Okay. All right. So a DAG is a directed acyclic graph. You don't know what directed is by now. I feel like I've been like really for a while. So like that's a little bit on you on this point. But acyclic, acyclic is a whole thing, right? Okay. So I'm going to reason about this not necessarily in the simplest way. I'm going to reason about it in the way that hits the most learning objectives, things that I think you might see in an answer to a Stack Overflow question or something like that at some point in your life. The set of edges is a set of pairs. In the case of a directed graph, we are now saying that is a set of ordered pairs. A set of ordered pairs, if the elements of the ordered pairs are all the elements of the same set, is a homogeneous binary relation. What is a homogeneous binary relation? A homogeneous relation is a relation from a set to itself. In this case, the edges are a relation from the set of vertices to the set of vertices, right? So there's from a set to itself because they connect to other elements of the set. It's binary because it has 2 elements. Addition is not a homogeneous binary relation because you take 2 numbers and you get 1 number back. Negation is a homogeneous binary relation because you take an integer and you get a different integer back, but you can get from any integer to any other integer, right? So there are these sort of naturally occurring homogeneous binary relations, and the one I think of most common is negation, right? Now, let's what's another one? Squaring is a homogeneous relation, but not binary homogeneous relations. Square root is depending on what set you take it over, right? When I say relation here, I really just need a way to relate one thing to some other thing, right? And so I'm going to do that by just like writing down all of the pairs of things that relate to each other. This makes sense a lot more often with pairs than it does with other sort of mathematical objects like numbers. Because with graphs, oftentimes we're dealing with labels or things that don't have total orderings or partially ordered sets or something like this. And so it makes a lot more sense to say just for everything how it relates to everything else, right? And this was not too bad. I hope you experienced on the Hiawatha line. Relatively small number of nodes, relatively small number of edges. And in fact, even if you're Amtrak, right, you can probably hire an intern to convert that entire thing into JSON graph in like an afternoon, right? That's why God invented interns, right? I am going to use the notion of a closure, and specifically the transitive closure. I'm going to take a transitive closure over a homogeneous binary relation, and I'm going to use this to argue about cycles and directed acyclic graphs. And so the homogeneous binary relation is a type of relation, and a closure is an operation I can perform over a relation. I'm specifically going to be performing the transitive closure, which is a way to take a relation that does not necessarily have the transitive property and add some stuff to it until you get the minimal relation that contains that relation but also has the property of transitivity. And the property of transitivity is not too bad. We're going to find it regularly, but it's basically if A to B and B to C are in your set, then A to C are in your set. So the transitive closure of the edges in Amtrak are the cities from which you can get from one city to another in Amtrak. In the case of Amtrak, every city is in its own transitive closure, right? But it could be the case that maybe all the rail lines going across the Rockies break down in like a bad winter storm or something, and then you no longer have a transitive closure. I was trying to remember the other day. Do you all like super into like the golden spike when you were growing up? Or was my father just an engineer? But I guess a lot of people got really excited when the first railroad crossed the United States. And they put a golden spike there. But currently the park is closed. And I guess it's in Box Elder County, Utah. Yeah, right. Oh my gosh, it's by the person that named Stanford after one of their children or something. Anyways, Sacramento. We were talking about Sacramento earlier, right? Okay, it's full circle. Okay, so real thing that actually happened. What year? 1869. Cool. We love golden spikes. Okay. So, the golden spike is the transitive closure of Amtrak. In order to define a homogeneous binary relationship and also a transitive closure, I'm also going to introduce another term. This is just something else I think you should know. It's called the Cartesian product. It's named after the food cart pods in Portland, Oregon. So a lot of people don't know that. Before Portland, Oregon existed, actually, they didn't have Cartesian products. There was no way to multiply sets by themselves. It is the set of all sets of pairs of some set, right? So it is the most permissive relation. So a relation R over a set S is a set of pairs of elements of S. Okay. I denote this using the times, which I usually pronounce as cross, which is odd. I don't ever know how to say that, right? In LaTeX and HTML, it's both times. As you all know, and I think it's just important to expose this to students, I was extremely into doing all of my mathematical notation with HTML until I had to write a ratio, which was just completely impossible. You could do it with like pixel specific precision in divs, and I was like, what am I doing? But this is an example. So you can say S cross X in LaTeX, and that's just a LaTeX formula stylized, the times element, and then S. This is a slightly different S. See, we're seeing it's actually coming across as a different character. And this is just an italicized capital S, the HTML times code, and that's just a Unicode character, right? And another S in HTML. So you can express the Cartesian project, I think, quite elegantly in both languages. One of the things that I couldn't do today was the big intersection and big union. Those are really hard to do in HTML, for example, but I can do little ones, no problem. So you can do quite a bit of set theory in HTML. And the example I'm going to use for all of this is colors, and I'm going to do colors in two ways. I'm going to do colors with respect to traffic lights and colors with respect to wavelength. And we're going to do that after we beat all of the MBAs to dinner. Go, 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 go. You're not going. You're not going. Okay. Ah, pausing. People have underestimated a critical ally against fascism, gamers. Okay, and with that, tell you what, those tariffs were announced on the Switch too, and that lasted about 3 days, and they're still on everything else. Okay, I don't know why the gamers are the most powerful political faction in the United States. I would have picked like the NAACP, right? That was I was like, I got one ready, and they're like, how about gamers? And I was like, no. And then, colors. Um, Whenever I talk about colors, I always think of Blue by Halsey. Great song. Um, Everything is gray. His hair, his smoke, his dreams, something like that. Great music video. Check it out anytime. Um, Anyways, as we know, there's exactly 3 colors: green, yellow, and red. Green, yellow, and red. Green, yellow, and red. And the reason for that is because traffic lights have the colors green, yellow, and red on. Yeah, right. You fool. You absolute. um, yeah. So we take a set. I'm going to call it the set of colors C, and it's GYR. No order, right? That could look like it's ordered. It's not. It's at least not alphabetical, right? The Cartesian product is the set of all pairs. 3 colors, 6 pairs, all directions. Yeah.
But
So currently we're in ordered world because we're talking about directed acyclic graphs. And yeah, so that's an essential piece of context, right? So specifically in a I said homogeneous hymenary relation. Binary homogeneous relation. So yes, in this case, and in fairness to you, that means that all of these standard parens should be curly braces because these are just sets. Right? Order matters. So how do we get to a relation from the Cartesian product? Well, first of all, the Cartesian product is a relation. It is the universal relation where everything is related to everything else. So it is an unrestricted relation, and usually for that reason, it's useless. If we're just going to have something with a universal relation, you usually just don't have a relation at all. We say we just use the elements set directly, right? So for example, we could relate green, yellow, red to green, yellow, red. I don't know, it's not too exciting, right? Non-trivial relations, so relations that don't contain the entirety of the Cartesian product, are simply subsets of the Cartesian product. So we take some of these pairs, but not all of them, and they form our binary homogeneous relation. I'm going to construct the traffic light. Why do I keep saying binogenous? That's not a word. Ring, 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 ring. Binogenous. Boop, doop, doop, doop. Okay. Sorry, I've spent too much time on the internet. Do you all follow the streamer drama with iStubs and H3 Productions and the new content cop that came out yesterday? Denim's TV, largest Hassan. Hassan? Yeah, okay. Well, anyways, it got real spicy yesterday. Okay. And I was definitely working on these slides and not watching Twitch streamer drama. I just love drama, right? And so the problem is if there's not enough drama out in the world, then I start starting my own drama, and everyone hates that. Okay, so we're going to construct L, the traffic light relation. What is the traffic light relation? I'm not really a traffic light designer. My sense is they probably have one thing that they're trying to avoid that's very bad, which is a hard transition from green to red. I think that in theory would cause people to like slam on brakes or go through a red light or something, right? So I'm assuming they have the constraint no red without prior yellow. So for all yellow to X that are in the light, X has to be R. Oh, that's different than what I said. That's saying if a light becomes yellow, it doesn't go back to green, which is also probably bad. Presumably you don't want a yellow to green, right? I think the other thing that you need with traffic lights, and my impression is that city planners don't think about this enough in cities other than Portland, because in Portland no one likes to go. But I was driving around Atlanta recently, And I think if you put up too many stop signs, people just like stop stopping at them, right? So one of the things you want to keep in mind if you actually want people to like sort of buy into your system of stoplights is you have to make sure that they become green eventually. And so I have formulated this as the requirement that you must be able to go through every color. And the way you go through every color is you either go from a color to that color and you go from to that color from some other color. So for all X in the colors, there exists Y and Z instead of colors, such that X precedes Y and X follows Z. So there is a color before and a color after every color. Not too bad. I put these constraints together and I put on my thinking cap and I thought really long and hard about things. And I came to the conclusion that this is the traffic light relation. Green must precede yellow, yellow must precede red, and red must precede green. And I'm going to call this relation L, and I'm going to note that this is a subset of C cross C, the Cartesian product of the colors. Okay, so this is monogenous, but how? B and H are completely different letters. It's okay, it's a monogenous high-married relationship, whatever. So, okay, should we break them down? So homogeneous, genus, the same thing, right? Homo to itself. So sets to themselves, and then binary, just two elements, right? Monogenous hymenary. What's your favorite word in this class that you don't know? See, I think I've tricked you. I think you know all the words and you just think you don't. Yeah. Yeah, now you know everything. Do you feel more powerful? Yeah, that's why I thought you. Okay. Um, this is a relation. We can express these using function notation. Functions are a subset of relations. They have more rules. But we can say the light of G is yellow. Why is that? Because if G is on a traffic light, the thing that is followed by is yellow. We could also equivalently argue we go in the other direction, right? So you can stylize these in a few different ways. I probably prefer infix notation for this because I want it to look like G is before Y with respect to the light relation. This is my favorite way to do it. I've tricked you. We were doing linear algebra the whole time. I know this has probably happened to you a lot more in Data 505 than it has in this class, but it turns out graphs and matrices are the same thing. You just have to like squint at them a little bit. Did y'all learn neural networks yet? Okay,
A
little bit. Right. So big neural network is always trying to trick people. You're like, okay, I got a bunch of neurons. And you're like, okay, what do you have with the neurons? It's like, they're connected to other neurons. You're like, that sounds like a graph, right? You got nodes and edges. They're like, no, it's a matrix. And you're like, oh, you got me again. It was another matrix, right? Here's the matrix. So G on the left side precedes yellow on the top. Y on the left side precedes red on the top. Red on the left side precedes green on the top. And so, you can think of this relationship in either direction, right? But in this case, we have the preceding color on the left and the following color on the top. And it's easy to rotate a matrix, right? So that's not a big deal. Blah, blah, blah. This is 9 bits, right? This is not that much information. This is a very small amount of information. That's 3 ones and 6 zeros, right? We can pack a lot of information, but yeah, the traffic light relation is 9 bits. There's another place that colors exist, and this place also only has green, yellow, and red, which we can see by looking at it and selectively only perceiving the green, yellow, and red, right? Which is how I always look at rainbows. So I did this in an undergraduate classroom, and they like all knew physics. So I'm hoping none of you know physics, because this is way harder if you know physics. Okay. So there's wavelengths and there's also energies, and colors have both, and they're anti-correlated. And so I don't know if red has more wavelength or more energy than yellow, but it's one of the two, right? Moving on. We've noted when we think about our rainbows, which we all love, right? We've noticed that red is higher than green. No, wait. Is that what? Red is higher than yellow on the rainbow. I'm going to say some imaginary made up words that might sound like colors, but we're going to remember there's only 3 colors. So when I think of the rainbow, I think red, orange, yellow, green. Okay, so orange, that's a made up word, right? So we've got red, yellow, green. So that means red is over yellow and yellow is over green. Okay, is that what I have here? Probably something like that. Yeah, okay, so top is over. So red is over, red on the top, R is over yellow on the side. And then yellow on the top is over green on the side. So we have the relationship in that direction. And so if we perceive the relationship in the other direction, that's probably the energy direction or something, right? What is interesting about this is that this is another relation. This is the rainbow relation, but it is still over the same set. So I've constructed 2 distinct homogeneous binary relations over the same set. Why have I done this? Well, we are in directed acyclic graph world, and one of these things is going to have cycles in it, and one of them isn't. And how are we going to get there? Anyways, I specified this. I'm using B because R is taken, because I used R for the color red. I think that's wrong. I think I should have used lowercase r for red to avoid this namespace collision. But I'm using B for the rainbow relation. The rainbow relation is a subset of the Cartesian project that contains red is more of something than yellow, and yellow is more of something than green. Now, an astute learner will note that I've been saying above or more or something like that, which means that this relationship is also preserved between red and green. Now, with Amtrak, I took some effort to specify that I was talking about atomic connections, right? So we are deviating from that here and now, okay? So how do we deal with this? Well, we're going to introduce the notion of transitivity. Transitivity is not too bad. This is the formal definition. I think the formal definition is probably easier than anything else. But if A and B have some relation, and B and C have some relation, then we take that A and C have some relation. This differs from friendship, right? You can be friends with someone that is friends with one of your enemies, or you all can do this. I don't do this. I cut people off. I have no fake friends. But some people have fake friends, right? But this is true in the case of, for example, integers and greater than. 1 is less than 2, 2 is less than 3, and 1 is less than 3, right? So some relations are like this and some are not. In this case, I am noting that red is above green on the rainbow, and therefore should be an element of the rainbow relation. Okay? This is transitivity. This is the application of transitivity. Now, I was going to use this to construct a closure, and I'm going to point out that this initial relationship is not transitive, and how do I make it transitive? And we can apply this the same way to Amtrak. The transitive closure of Amtrak is the connections between all cities, right? So when we take something that is a non-transitive relationship, we can promote it to a transitive relationship with this closure operation, and it's going to have 3 different steps. This is an operation over sets, but it is specifically an operation over sets of ordered pairs, which means it is an operation over sets of sets of sets. We're going to take a set of sets, and we're going to make another set of sets. But the set of sets that we're making is going to be a binary homogeneous relationship with the property of transitivity. Okay? We're taking a set of pairs, we're going to add pairs to it, and that's going to cause something to be true of all of the pairs collectively. I'm going to introduce the terminology r raised to the power plus, and I'm just going to say r plus for that. It is completely reasonable, as I've done here, to stylize this using either LaTeX or HTML, of course. Okay. There's only going to be 3 requirements for this thing. Given some why do I keep saying binogenous? It is a fun word to say. Okay, so given some binogenous relationship, they're not even relationships, they're relations. I'm like shipping these 4 colors with each other, right? They're like, I'm an inanimate object, I'm a platonic ideal. Okay, so to go from a relation to its transitive closure, how do we do that? Well, we take the relation and we take some superset of the relation. So every ordered pair within the relation will be part of the transitive closure. So everything that's currently related will stay related, okay? Then we're just going to use set operations. I don't know how much you've seen superset. I'm assuming a little bit. But basically what a superset means is that everything in the subset is also in the superset in the case of a binary homogeneous relation. The maximum size of the superset is the Cartesian product, right? And so that is the set of all possible pairs. And then the minimum size is the considered relation. So if you start with the Cartesian product, it's its own transitive closure. Sort of that follows from that, right? But how do I say this? For all x and y in some set, if x and y are in some binary, or, well, that's just R. If x and y are in some relation R that is part of the Cartesian product, then x and y are part of R plus. So we're keeping everything. We're going to add things. Okay. Yes.
I know you like to go super speed during this, but can you help us round this back into where this is fitting into the DAG?
Yes. So I'm going to build up here to a definition of cycles, and I'm going to use the transitive closure to show if an edge or a set of edges, like an edge which is a set of edges, right? If that contains a cycle. And on the way to do that, I'm defining transitivity, which is, in my view, separately useful to teach you an example of one of the properties a relation can have, right? And so I was hoping that in some way it would be of, I don't know, some like abstract or theoretical or cognitive benefit to you to see that set theory used in this way in support of building the directed acyclic graph definition. I'm also losing my words, which is one of the reasons I'm talking at a fixed speed. It's just the speed the words are occurring naturally, actually. I'm actually just a conduit of graph theory. A lot of people have personalities. Not me. Not me, I'm just graph theory. Oh, right. So, this is unrelated. We're just going to take a digression. So, you're all familiar with molecules and atoms, right? Well, we can think of an atom as being a graph, right? Because it contains elements, which are neutrons, electrons, and protons, right? And these are connected in various ways. So in the nucleus, they're connected by the nuclear strong force. I don't really know how electrons work, but I'm guessing there's some kind of edges there, right? So you think that's air you're breathing? It's actually graphs, right? It's graphs all the way down, I'm afraid. Okay. It's everything's a graph. This is an example of how we can add an element to the small thing, the non-closure, in order to extend up to the... This looks like I skipped slides. Was I goofing too much? Yeah, I'm missing something. That's fine. That's fine. Right. You take the set of pairs. The set of pairs is going to make some requirements of the overall set of pairs. And this is the pattern that matches the requirement. If A and B are in your... So for all triples of vertices, if AB and BC are present, then AC must also be present. And this must happen recursively, because if when you add AC you get something else, then you might need AD. So I'm going to take my set of pairs and I'm going to add pairs to it that should be present because of transitivity. And I'm going to keep adding pairs. I'm going to keep adding pairs, and I'm going to add pairs until the transitive property is satisfied over my set of pairs. Which means that if there was a chain of connections, now each set of that chain of connections has its own pair that corresponds to going from any point in that chain to any point else in that chain. And then looking at this with colors, with the color example, this was very simple, right? We just added red, green. And this is why there's only 3 colors, because it made this example easier, right? But if we had more than one color, we would have had to add many edges. We would have had to add an edge from red to every color, and we would have had an edge from every color to violet, and then some other colors in between, right? If we were going in the rainbow order. Lastly, and this is important because it's a little bit too easy to construct them otherwise, you must find the smallest possible relation that satisfies this. And why is that? The Cartesian product is always the superset of every relation, and it is always transitive. but we are not always looking for the Cartesian product, the maximally permissive universal set, right? On the rainbow relation, for example, we do not want there to be an edge from violet to red, because violet is lower on the rainbow than red, and we are looking for things that are higher on the rainbow. So you take the smallest possible relation. What this prevents there from being is there's no extraneous information. There's nothing that isn't represented by the edges that were in the initial relationship. And so just requiring this to be the smallest, this makes mostly a lot of proofs easier. Just to point out where we're going, I want to remind us that these binary relations are graph edges. They're the same thing. This is the usefulness of graphs. And also, we can think of all of these edges, especially directed edges, as pointers. And when we start thinking of things as pointers, this becomes really, really useful for us as systems programmers, okay? Graphs are all over the place in operating systems. So, how am I going to define cycles? With the benefit of transitive closures. I think this is the second easiest way to define cycles. The other way is with paths, and paths are kind of sketchy. So I'm going to consider a graph G, which is going to have some set of edges E. I'm going to note that E is a homogeneous binary relation, and I'm just going to take the transitive closure of E. Easy, right? Taking the transitive closure of E. In the case of Amtrak Cascades, I now have a Portland-Seattle edge, right? G contains a cycle, which is equivalent to having the property of being cyclic, if each contains an edge from a node to itself. If I consider something as simple as Amtrak service between Portland and Salem, there's a Portland, Oregon City edge, an Oregon City edge, Salem edge, Salem, Oregon City, and Oregon City, Portland. Edges going down and back up in both directions. When I take the transitive closure over that, that means I take out I can perceive myself as there being an edge directly from Portland to Salem, because I can take Oregon City out of that. And as soon as I perceive there's an edge from Portland to Salem and Salem to Portland, I notice that there is also a transitive edge from Portland to itself. That means there's a cycle. That means I can take round trips on Amtrak. Now, there are other things that we can store in graphs. And one of the examples is academic citations, for example, or even non-academic citations, right? There are no cycles in academic citations because no paper can cite anything that came out after it came out. So these are strictly directed and acyclical because there's no way to go back in time. You can only cite things newer than you. So we can have these arbitrarily complex and dense graphs, right? But they contain no cycles. If you take the transitive closure, I have probably transitively cited like Newton and Leibniz and the changing of ways, or like these like various ancient academic texts, right? But I've never cited anything that has cited me, right? Or I've never written a paper that cites something that cites itself, right? Now, I was trying to bamboozle academic publishing by citing a preprint of something in a paper that was being released and then updating the camera-ready version of the preprint to point back to itself. So I am trying to publish a recursive citation right now, and I will let you know how it goes. But to my knowledge, no one has ever done it before. And the benefit of this is as soon as you get the recursive citation, then you can write a paper on your recursive self-citation, right? So it's 3 papers for the price of 2. So I've been cooking on that a little bit. I'll let you know if I pull it off. But to my knowledge, it's never been done before. It's probably considered fraud. I mostly publish to IEEE conferences. The International Electronics and Electrical Engineers. You should know who the IEEE are. They're your professional society once you get an MSCS. Them and the ACM, but the IEEE is more powerful. And also international. Now, it is true that I can walk over to Union Station tonight and claim, aha, I have taken Amtrak from Portland to Portland. And that's called being annoying. Don't be annoying. So we're going to find cycles to be non-trivial, that you only get credit for your cycle if it goes through at least 2 points. Okay. Now, if I take the train to Oregon City and then come back, that's fine. That still counts. I still get credit for that, right? But if I just stand in Union Station and say, I'm completing a cycle, that's being annoying, okay? So don't be annoying. Or I mean, you can be annoying if you want, but with the benefit of directed and cycle, we have most of the graph theory terms we need. I am putting some terms on the board that you may see someday. I want you not to think too much about these terms, but just be aware they exist, and you will be able to look them up and understand them the same way you understood this. These are circuits, walks, paths, and trails. Of these, paths are the most useful. There's directed and undirected variants of all of these, and they correspond to trains and routes, is how I think of it. This is a DAG. It is a directed acyclic graph. It is made directed by the fact that there are arrows, and it is made acyclic by the fact that there are no loops going through the arrows. And if I took the transitive closure of this, I think this may already be its own transitive closure. Is that correct? No, there would be a B to E edge, right? I can go from B to D to E, but I would also need this edge. And I think that's the only one that's missing, right? This is just the example of a DAG from Wikipedia. So the transitive closure contains no identity. There's no A to A edge in the transitive closure. And there could be if there's an arrow from any of B, C, D, or E back to A. Then it would no longer be a DAG. And then it could no longer be a publication history, right? Because you could be citing something that comes out after you publish, which I think I can do. I think I found a way to time travel. You know this. Color wavelength is a directed acyclic graph. Why is that? Because every color has strictly more or less wavelength than every other color. So this is directed and acyclic. There is no edge from G back to R. R is higher than G on the rainbow, and G is lower. That's it. That's all there is to it. Fun fact, traffic lights are cyclic. That's why they call them light cycles, right? Yeah. You're like, oh no, I missed the cycle. Do people say that? Oh my gosh. So like, I waited at a traffic light and it turned green and then red and then it turned red again before I went through it. And my brain exploded. I didn't recover. It was pretty bad. Did I tell you all about my car trouble incident? Oh, so I knocked off half my skid plate on the way down to Salem, and I thought it was just like getting a rock stuck in my wheel well. I was like, why is my car making that horrible shrieking noise? And I looked under it, there's like a giant chunk of metal hanging out that I apparently drug down the highway for 40 miles. Anyways, I went to First Lube in Salem, which I highly endorse, and they fixed it up for me right before class, and I almost got to class on time. And that is the story of how I completed the cycle of Portland, Salem, Portland today. Thank you, First Lube. I'm not sponsored, but I have sworn my life to First Lube. I will do anything for them. I might even get my oil changed, which I don't usually do. So I think we've had some talk about Friends tonight. We all know Friends. Friends were invented by Ridley Scott in 1991 when he wrote the film Thelma and Louise, right? A sort of revenge comedy. So Thelma and Louise are friends with each other. Friendship is built on the basis of mutual enthusiastic consent, which is undirected, which means friendship does not form DAGs. Which means on Twitter, where you can follow someone without them following you back, you can't have friends, right? So there's no friends on the internet because of graph theory. I'm assuming none of you are planning on getting an undergraduate major in computer science at Willamette next year, but not to worry. All of the classes are a directed acyclic graph because no class can have a prerequisite that is also its postrequisite. And believe me, I also tried for that one. I was like, what if we update the requisites while they're in the class? And apparently that's bad and wrong. Okay. Trees. A tree is a special case of DAG, and it's not a particularly complicated special case of DAG. The trees are defined in at least set and graph theory, because there's relatively simple ways to make them out of steps without escalating all the way up to a graph. I would not necessarily encourage you to think of them that way. What this means is that by default, if you are studying graph theory, which I'm not thinking you're going to do, people are going to be talking about undirected trees. And they're also going to be talking about disconnected trees, which is a tree where not everything can get to each other. Big computer science solved this problem for us by getting way more popular than math. And every time a computer scientist refers to a tree, they mean a directed tree and they mean a connected tree. So I am letting you know that technically tree does not mean it is a type of DAG, but I have never seen anyone refer to a tree that is not a type of DAG, right? So I think that is a safe assumption. Trees are simple. They're DAGs where everything has at most one incoming edge. That's it. That's all there is to it. So on my ABCDE DAG, right, there were like 3 arrows going into C. That's not allowed anymore. You got to pick one. That's called choosing your favorite parent. That's not what it's called. I made that up. Do not put in the course of vowels. It's called choosing your favorite parent. Okay. But by convention, the incoming edges, the node from which the incoming edge originates is called the parent. And the destination of an outgoing edge is called the child. Okay. How did I specify this? A graph is a tree. Well, DAG is a tree if for all of the vertices in the set of vertices, there is at most one vertex that terminates. There's at most one edge that terminates at any given vertex. So less than or equal to 1, the cardinality of the set of edges that end at some vertex. Trees show up in a lot of places. This is a decision tree. I don't know what decision they're trying to make here. It's probably not that important. Major problem, 20%. Ooh, I don't want to go that way. Where's the good way? Video images. That looks good, right? So maybe you've seen decision trees on whiteboards at work or something like that, right? Here's another example of a decision tree. You can either case, proceed, win, loss, costs, proceed, settle. Oh, this is for case law. I haven't seen anyone else say this, but I'm completely 100% sure this is right. So I'm just going to throw it out there and we're going to see what happens. River systems are trees. And I think this is just an emergent phenomenon. I don't think this has to be the case, but I think it's highly likely that in the earth and sort of geological sciences, that if you have some river, by convention, tributaries will flow into one larger river, and that larger river will not split. They split a little bit, and so, like, for example, the Mississippi Delta is maybe that's like a split, but we also call that the Mississippi Delta. So I'm giving myself full credit there, right? This is the Columbia River system, and we have right here, there's the Willamette, and it goes into the Columbia. So every tributary flows into at most one other river. That river is its parent, so that means this is a tree. There's also these things called trees that are outside. I've never heard of them. Anyways, trees are also a data structure. Who loves data structures? Woo, data structures. Woo. Yeah, that's right. I thought I heard a lot of cheering when I put data structures on the slides. Trees? Oh, more than data structures? That's fine. I'll just... That's fine. Okay. Trees occur a lot in computing, not just in computer science. They occur in other disciplines as well. Generally speaking, if you start studying why you have a tree, it becomes computer science pretty quickly. Why is that? Well, a lot of times we want to store some data, and we really only need one way to get there. So we can ask ourselves maybe a series of questions about the data and say, it's this way, then that way, then the other way. This is how the operating system organizes memory in page tables. I think you mentioned Professor Cordoba is drawing a B tree on the whiteboard, so this is how SQL databases store things. They store things in B trees. We're going to do something a little bit different than data storage in this application. We are going to instead assure integrity. And the way we're going to do that is we're going to take hashes of things. But to verify the integrity of something, we only need to hash it once, which means that we can use a tree. We only need one hash of everything we need to hash. So we only need one parent. And I know what you're thinking. You're thinking, wait, how does a hash correspond to an edge? Not to worry, we'll get there. Just a few examples of what this might look like in code. This is maybe the most basic version of a tree. I do want to point out here, absolutely nothing is enforcing that this is a tree. There is no way to enforce I have at most one incoming edge. And see, that is a ludicrously hard problem. It can be done. It's not easy, right? And so what I do, I have some untyped data storage type. And then I have, this thing is essentially a Pascal array, right? It is a length prefixed array of pointers. And I call the things children by convention. The most common type of tree that I'm aware of is the binary tree. Binary trees are very nice because you can true false index them. I wrote this pretty interesting implementation of a binary tree in Python where you compared the value of a key to the root, and then you used the result of that comparison as the index of which child you go to. That's cool. You can kind of only do that with binary stuff, right? So the binary tree is most commonly taught in undergraduate curriculum as the binary search tree, where you just order integers, but you can order them however you want. It is very common to do left and right. Now, of course, if a tree only has 2 children, you can still have a tree of arbitrary size. So this is the most general and simplest tree. And by convention, we refer to the sides as left and right, and then the parent-child relationship is up and down, right? And a lot of people are confused, but this is in fact how you spell right because it has to have the same number of letters as left. So I feel like I got more negative feedback about my spelling choices back when I seemed more apologetic. You all just kind of seem resigned now, and I respect that for you, right? No one can force me to name variables anyway. I don't want to, right? I'm writing my own code. I should note that you can definitely implement list t using this. All you do is you get rid of the right or of the left, right? So what does this mean? Well, actually, that means that a linked list is a one-array tree, that's pretty cool. Okay, so I've tricked you, I've bamboozled you, you've already implemented trees. So smart. Very cool. BST. Do y'all know what BSTs are? Yeah, okay. We'll do Merkle trees. They're on the next slide. What's a Merkle tree? You have a hash. You hash your 2 children. The hashes of your children are hashes of their children. And you keep going on hashing children together. But at the bottom, what you have is the data you're actually trying to verify the integrity of. And these are the data blocks. In the case of blockchain, this is a transaction, this is a transaction, this is a transaction, and this is a transaction. So you have your transactions, which is I give someone n amount, right? You hash that, then you hash the pairs, and you keep hashing up. The goal is to get down to one single hash that you then throw into your blockchain, and you only have to store 256 bits to know not all of this information, but if you already have this information, you can verify the authenticity of all of it with only 256 bits, and it is extremely difficult to falsify. Because if I lie here, it breaks everything, right?
Question.
Mhm.
So is it like a piece that's going up?
It really just depends on how you think of the relationship, right? Sure. Maybe it's an undirected tree. I don't know. They are called Merkle trees, and I do think that I'm not going to implement them with pointers, so there isn't really a notion of direction at all. But I am going to refer to this as the parent. Here's some tree terms I'm going to introduce. Connected we'll never see, but all the other words I have to use. Trees are connected. If we take the transitive closure of the edges, there exists a node that has an edge to every other node. It is not the case that every node has an edge to every other node in an undirected case, but there is some edge. There is some node that has an edge to every other node. Connectedness is usually defined over undirected graphs. In this case, we can do it over directed graphs as well. Now, if you take the transitive closure of the edges, and there is one node that has an edge to every other node, that node is the root. So the root has a way to get to every other node. It might go through other nodes on the way. It might go directly to that node on the way. We don't worry about it too much. I haven't seen this term. I introduced the term ancestor. It is either the parent or the nth degree parent of every node. The Merkle root of a Merkle tree goes in the Bitcoin block. So the root is what is stored in the block. A leaf is a node with no outgoing edges. There pretty much must be such nodes, right? Because no cycles are allowed and we have to get to every edge. So there's going to be, we have to get to every node. So there's going to be nodes that don't have outgoing edges. As we progress through Merkle tree and heap, I'm going to start saying node, leaf, and root as if they refer to three different things. That's not true. A leaf is a type of node. A root is a type of node. It is often helpful to say leaf, node, root. And node just refers to the things that are neither leaves nor roots. Okay. Here's a diagram. 2 is the root. This 2. This 2 is a leaf. I could not determine the convention on whether you used the regular or irregular spelling. And so the regular spelling is L-E-A-F-S, because that's how you would spell it conventionally. But if these are supposed to be pluralized the same way leaves on trees are, then you would do L-E-V-E-S. I don't know how you're supposed to spell it, so I just start spelling this completely randomly. So all of the spelling of leaf through the rest of my slides is just... Okay. Parent-child. The parent has an arrow to the child. That's a very helpful term. Height and depth. Trees have the same height and depth. The height is the maximum number of jumps to a leaf. The height is the maximum number of jumps from a leaf to the root. Of course, those are going to be the same number of jumps in both directions. This thing has a height and a depth of 3. Now, we don't only use height and depth to refer to trees. We also use it to refer to nodes or leaves, right? So this is the node 3. 3 has a height of 2. Why is that? Because if I consider 3 to be the root of its own tree, that tree has a height of 3. Or no, height of 2. Dang it. Yeah, 3 has a height of 2. Okay, whatever. Okay. 3 also has some depth. It is easier to consider depth in the case of 4, though. The depth of 3 is 1, which isn't too exciting. If we take some node and we imagine it as a leaf, so we disregard its children, which you should never disregard children, but that's why I was looking for other terminology, right? Okay. So we're going to imagine that 4 doesn't have any child nodes, right? And we're going to say, okay, well then what is the depth of the tree? And so it has a distance of 2, right? Size is what you would expect. There is one time this is going to be really useful. I do not know a term to refer to the number of leaves. I would maybe go for like leafiness, right? But I really needed one. I don't have one. And that's the easy part of today. Okay, let's go to the fun part. Any questions? These trees are named after Angela Merkel. That's not true. It's a different spelling even. Where are we? Okay. Jumping right into it. Blockchain is a one-array tree. Lists are a one-array tree. They're a one-array tree because they're directed acyclic graphs and everything has at most one child. Okay? We can also call these sequences. I don't commonly do this. I usually reserve the term sequence for numbers, but we could put them in an array. Why are we thinking about this? Well, someday you might want to implement blockchain, and probably the way you're going to do that is going to involve writing blockchains into files somehow. Maybe you have access to an SQL database, but I would consider that cheating because I don't think you've implemented an SQL database in C89. So don't even think about it, right? Okay, that's right. If you want to store your blockchains, you write them to a file. as Linus Torvalds intended when he implemented the Linux kernel. And I know what you're thinking. You're thinking, isn't it cheating to use the Linux kernel? The answer is yes. You were also supposed to implement the Linux kernel, but I didn't make you do that, right? So why am I suggesting this? Well, there might be a way you need to write these to files, and I'm recommending that you just line them up in an array and block like write the array. That's how I would do it. How does this work? Well, in the one array blockchain chain, we first have a Genesis block. Did you all get that? This says Genesis block. It's named after the band Phil Collins and Peter Gabriel were in, right? Yeah. Okay. The Genesis block is hashed into the previous hash of the first block, which is hashed into the previous block of the next block. Oh, what are all these transactions? Oh, we'll deal with that in a minute. Okay. List T is a one-array tree. Presume we've all done list T and feel good about it. I haven't looked at any of them yet. One student in the MSCS program already did the heap T assignment, which I thought I hadn't assigned yet. But I got, someone was like, I finished heap T, and I was like, but why? So anyways, I want you to know that one of you is a huge nerd, but I can't tell you who it is, right? It'll be a different person than who you think about, actually. There's actually multiple huge nerds in this class alone, right? Yeah, it's a huge problem. So I mind controlled myself into wondering if there was a cycle here. So this is a directed edge from HDMI to USB 3, right? But I don't think I can close the loop. Right, sorry. So I perceived there might be a cycle. Okay. At exactly 7:42 every Monday, because it takes me 12 minutes to walk to Archive Coffee Plus Bar in Salem, Oregon, I release the data 505 students to their own devices, and I walk in and I order a mocha, and they say, hot or cold? I say, hot. And they say, small or large? And I say, small. And what we're doing is we are verbally communicating a tree structure, right? And the tree is a decision tree. We learned a cute thing. We were trying to figure out how to make my ordering easier. And so we determined that because I always order a mocha, oat, to go, hot, small, we can call that moths. So now I just go into Archive Coffee Bus and do a moth impression, right? And then yes. So we have a lot of fun down there. Salem. There's a lot of reasons to be in Salem. Okay. Trees, our case, transaction review. Transactions are trains of ownership. I'm going to just like throw some code at this problem to make it a little bit more explicit what we're looking at, and then we're going to start hashing. Okay. So a transaction review contains a sender, a receiver, and an amount. The sender is the person that already had the coins. In the case of Bitcoin, the initial owner of all of the Bitcoins is Satoshi Nakamoto. So at some point in time, your coins belonged to an imaginary person, right? And then there's some chain of ownership that involves some cyber criminal transferring them to you, right? And it is not true that everyone with Bitcoin is a cyber criminal. We just don't have an example of someone that has Bitcoin that isn't a cyber criminal, right? Does anyone in here have any Bitcoin before I?
I had $150 in college.
Okay, so you're safe. You're no longer a cyber criminal. Okay. So the correct answer is no. All right. Okay. I was very proud of all of you for investing wisely. Sell that. Okay. Sender receiver. I often say, there's the person that sends the Bitcoin. No. People don't send Bitcoins. RSA public keys send Bitcoins, right? Now, a person can have an RSA public key, but so can a bot. And one person can have 1 billion RSA public keys. There is not a strict correspondence. They don't have to be people. They can be scripts. They can be cron jobs. They can be websites. They can be the NSA. So I always have to be careful and remind myself, no, these are not senders and receivers. Now, usually, so I learned all of my network theory on the example of you make an instant messaging app. It's like a natural thing to do, right? And then, yes, on that, everything is a person, right? But now these kids these days, they're hooking up their instant messaging apps to LLMs, right? And talking to robots, right? Disgusting. Okay. So here's how I make a transaction. I have some key size and I have some integer size on my system. I happen to use a 64-bit integer, but I allow that to be changed because I don't want to have too many magic numbers. Now you'll notice I still have a 64 in there, and we'll get there. So the transaction structure is the sender modulus. Why is it only the modulus? Well, your public key is going to be 65537, so the only thing you actually have to share is your modulus. The modulus is the thing that is 4096 bits in size if you do 496-bit key generation. So you need a 496-bit entry to store the sender public key and the only components of the sender public key you care about, right? You need the exact same thing for the receiver public key. And then you need the amount. Why is the amount a 64-bit? Well, as far as I know, there are 2.1 trillion or 2.1 quadrillion divisible units of bitcoins. That's 21 million bitcoins, and they're divisible in like 10 to the 6th satoshis or something. So you probably have some number of satoshis, right? Anyways, the maximum number you can transmit is around 2 to the 50th. So I'm storing that directly in a 64-bit integer because I know I'm allowed to do that. Right, so the only integer size I'm hard coding corresponds to a specific numerical value that I have to store, right? Now, in order to create a transaction, I have to package this thing up and I have to do a few things to it. So this is a transaction, so I need to digitally sign it. The way I'm going to digitally sign it is I'm going to take my public key, which I've already thrown in this transaction, and I'm going to create a ciphertext using my private key. And I'm going to create the ciphertext of this sort of transaction structure. But I'm not only going to create that ciphertext, I'm also going to create an SHA-256 hash of this entire structure. I'm going to release both of those into the world at the same time, and I'm going to put my public key on top of it. So people can take my public key, they can unencrypt the ciphertext, and they can compute the hash of it and see that they all line up. And that's what makes it my Bitcoin that only I can spend. Now, there's one little problem with this, which is that my public key can encrypt things up to 4096 bits in size, and it's encrypting more than that, which is a problem for chunks. We all love chunks, right? Remember chunks, SHA-256? Yeah, learning objective achieved, right? So 64 plus 64 plus 1 is the size of this thing. Nope, not this thing, this thing. This thing's going to be about 64 words in size. This is going to be about 64 words, right? So it's big, right? So this is how many 64-bit words we have. The 64-bit words are, of course, bigger than bytes. They're bytes to bytes, right? 64-bit key, 64-word key, 64-word key, 1 word amount. That adds up to 129, which is, of course, as we all immediately recognized, a multiple of 3, right? So it's bully for us, right? We can only encrypt things up to size 64 because that's the size of our modulus. And if we encrypt things bigger than that, we start clipping off information and losing granularity, and we can no longer successfully decrypt. So I simply took this 129 and I split it into the largest chunks that I could still use, which is 3 chunks of size 43. Cap is divide evenly. If it didn't divide evenly, I was going to divide it anyways, right? I'm sort of a divide and conquer type, right? Remember when I made you all implement long division? That was awesome. One student came up to me after class and was like, I implemented long division. I was like, yeah, that's cool. That's what really gets you in the heartstrings, right? Did you all enjoy implementing division? Okay, there is a right answer to that. And it's... Mine has a memory leak in it, which I don't know how because it doesn't malloc. That's crazy, right? Like I put it in Valgrind and Valgrind's like, what are you doing? I was like, if I knew, right? Okay. So what are we gonna do? All right, let's talk through this. My public key, the 3 chunks, I encrypt each of the 3 chunks separately with RSA, and I store each of the 3 chunks, so I have to run RSA 3 times. So I do key generation before this, and then I store the hash digest. Anyone that gets this message can take my public key, unencrypt each of these 3 chunks, and verify that they hash the value. Easy peasy, right? I would go so far as to say it's lemon squeezy, but that seems excessive, even for me, right? Okay. This is a summary. We make a transaction structure. We cast it into a 64 T array, probably. We RSA encrypt it, and we also SHA hash it. We package this up into a signed TX struct, and we prefix it with the public key. That's how you make a transaction. These are the transactions that are going to be my data blocks inside my Merkle tree. Okay. I need to be confident that no one fiddled with my transactions. I don't want anyone impersonating me, and I don't want anyone changing the amount that is in these sort of things, right? So in order to deal with that, we're going to have to solve this problem somehow, and we're going to solve this with an ungodly number of hashes, right? Yes.
In your original tree example, where the blocks at the bottom, those are the overloading block, where the rectangles at the bottom representative of one block. Like in L1, L2, L3, L4, all are one block.
These are transactions.
Okay.
All of these transactions are in one block because the top hash is in one block.
Okay. And when we're saying block, can you define like what the boundaries of that are?
A block is the hash of the previous block, the Merkle root, the timestamp, and the timestamp determines the point at which the transactions are finalized.
Okay.
And then the number that is used once, which is what makes the fixed number of leading digits on the next hash satisfy the proof of work requirement.
I didn't catch that last part, but I'm sure you'll come to it again.
Yeah.
And each block is connected to each other and it's the block.
Yeah, they're connected by the hash of the previous block is in the current block. So it's hashes all the way back to the genesis. These are transactions. This is a component of the block. It's, I have some pictures at the end. Maybe that'll make more sense. And maybe it won't. We'll see. Okay. We're going to use a Merkle tree to solve this problem because it is unreasonable to put an arbitrary number of hashes in a blockchain block because we have to distribute these blockchain blocks over the internet. We don't want to be sending arbitrarily large amounts of information. So we're going to move the Merkle trees and the blocks separately, and then we can transmit the Merkle trees more than once, but we want to get everyone sort of mining on the blockchain pretty quickly. So we're going to move them separately. So in order to have confidence in these transactions, we're going to do these big hash structures up into a Merkle root. We're going to store the Merkle root on the blockchain, and then everyone will be confident in the integrity all the way down. Is this system foolproof? Probably not. It doesn't seem like a lot of falsification happens on it. This is what it looks like to me. I have a series of transactions at the bottom. These are not leaves. These are kind of something else. These are the leaves, because the Merkle tree only contains hashes. But these hashes correspond to some transactions, right? You can think of them as leaves or not. I prefer not to think of them as leaves because I prefer to think of the Merkle tree as a binary tree, where everything has two children, right? And each of these hashes is one child, right? So we have a hash of every single transaction. We hash all of the pairs of hashes. We hash pairs of all of those, and we continue hashing pairs to get fewer and fewer overall hashes until we get to a single Merkle root. This can be quite inefficient because all of those edges can be pointers, but they don't have to be pointers. And I'm going to use the example of the heap data structure to demonstrate to you how they don't have to be pointers, okay? There's going to be a lot of hashing, but before there's a lot of hashing, we're going to put all of this stuff in an array. So we love arrays. I'm introducing one additional term to refer to trees. This term is complete. It is complete relative to, I think I call them like arities, but a binary tree can be complete. And what makes a binary tree complete is that its sort of last layer is filled out all the way. And when we say filled out all the way, either that's filled out all the way across, which is a little bit too strict because then we can only have power of 2 numbers of transactions, or we say all of the leaves are as far left as possible. So we push all the leaves to one side. And it doesn't actually matter which side it is, but they're all pushed to one side. So let's look at a few examples of this. This tree is complete. It is complete because every node has 2 children or is a leaf. Very simple. This tree is also complete, and it is complete because the last layer is as far left as possible. This tree is also complete because the last layer is as far left as possible, and above the last layer we have an inarguably complete tree. So you can always take a complete tree, remove rightmost leaves, or add leftmost leaves. That's fine. This tree is not complete because it's missing a left turn leaf. Left turn? Sure. It's missing a left turn. Here we are on the left turn coast. Okay. It's missing a left turn leaf. I wonder what I was trying to say. Because yeah, maybe. Because the thing I went to after left turn was lefterly, which is also not. Okay. What is the benefit of having complete trees? Let me let you in on a little secret. Big computer science doesn't really want you working with pointers. Because we've noticed every time we give the humans pointers, they give the computers segmentation faults. And when you give your computer segmentation faults, then I start getting questions in my office. They say, who taught this person to program? And I'll be like, we tried to do memory safety for 10 weeks, and they're like, then where all your segmentation faults come from, right? So I'm going to try and have fewer pointers. Am I going to get fewer segmentation faults? Probably not. I bet there's still going to be a lot of segmentation faults, but we're going to have fewer pointers, right? A complete tree, like this one, you can place this thing directly in an array. You place the root in the 0th location, then you place the first row serially. So 1, 2, 3, 4, 5, 6, 7, 8. Easy. 1, 2, 3, 4, 5, 6. Easy. 1, 2, 3, 4, 5, 6, 7. Easy. Just place them layer by layer. If you have heard the term breadth first search, that's what we're doing here. This is a good one. So we do 1, 2, 3. Ah, this is segmentation fault. Oh my gosh, I just segmentation faulted myself. Oh my gosh. I'm gonna call up my CS professor. Complain that someone segmentation faulted me, right? So anyways, if you've never experienced a segmentation fault in real life, that's exactly what it feels like, right? I hope you all had fun. I feel terrible. Okay. Just leave spelling watch. Okay. We're still struggling. This is one way to do this. You may be tempted to do this. And sure, that's bad. Instead, we're going to introduce the heap data structure. It's famous for being heaps of fun. Yeah. Wake up, heeple. Okay, all right. This is the heap data structure. I hemmed and hawed greatly over the way to introduce Merkle trees because they're just kind of weird. And I was like, how do people teach complete trees? I realized everyone in the universe teaches heaps. Have you all seen heaps before? Okay. The heap seems to be falling out of favor a little bit. It was taught more commonly in computer science programs back when we were stricter about teaching everyone operating systems, because the heap is so often used to implement a sort of technology called the priority queue that for a while there, people just said priority queue to refer to heap even when they weren't keeping track of priorities. And then at some point, people started using things other than heaps to store priority queues and kept referring to them as heaps. And so it got kind of weird. In an operating system, this device is running an AMD 64 instruction set architecture, and it's running the Windows operating system. When Windows runs on an AMD 64 operating system, every single thing that runs at one of 4 different privilege levels, and they're just 0 index. So 0, 1, 2, 3. That's it. 0 is used for the kernel, and 3 is used for all the stuff I do. And 1 and 2 are actually not used because all the operating system engineers found out they would rather maintain 1 bit than 2 bits that determine privilege. So there's just 2 bits that sit there and look pretty, right? There's 1 bit, right? So you have 2 bits, and they just always set them to the same value. My operating system, which tells me often that it works very hard, see, it's asking to be activated at this very moment. It's responsible for deciding who gets resources. And one of the entities that sometimes gets resources is me. Sometimes when I open my web browser, it actually opens and starts running. And sometimes someone else is using my computer at that time. The person using my computer is Microsoft Windows. I am acting at current privilege level 3. Microsoft Windows is acting at current privilege level 0. And we both submit requests to the operating system for resources. All of Windows's requests are at priority 0, and all of mine are at priority 3. Windows stores all of these things in a heap, and every time it has some extra free time to work on something, it takes things off the top of the heap. And whatever has the highest current privilege level is the thing that gets the next permission, right? This is why sometimes it's very hard to get your computer to run when it's trying to update itself. That's because that has higher privilege than you, so it's getting all of the system resources. That's sort of where heaps, I think, wormed their way into computer science. I don't really see them used that much more often. So I'm only teaching them to you as a way to explain how Merkle trees work, and to sort of fiddle around with Merkle trees a little bit. The heap is an extremely high performance data structure for this specific application and not for anything else. It can be used in heap sort, which is a relatively fast sort, but not fast enough that anyone actually uses it. And it is a very interesting application that it is a non-linear graph that can be stored linearly in an array. And I don't actually think offhand I know of another example of such a data structure. So how are we going to do that? I just talked about priority for 10 years. We're going to make a heap. I'm going to step through the operations of making a heap, and then at the end of it, you'll understand heaps and Merkle trees. That's the plan. We'll see what happens. Okay, so I'm going to start with an empty heap. This is what you, so I think frequently as humans these days, we're like busy, but imagine you're like my cat, right? So my cat has no responsibility. So my cat's priority queue is currently empty, right? So this is a picture of my cat's priority queue. There's nothing here, right? Now, they often seem to think they have business to attend to. Sometimes they like run. And I was like, where are you going? You don't pay rent, right? So this is an example of an empty heap. Now, oftentimes I give my cat things to do, and I always give my cat things to do in the form of integers between 0 and 255 inclusive, right? So when I get home after class tonight, I will go to my cat and I will say 128, and I will specify that I'm using decimal before I say this, of course, because I don't want my cat to be confused. So the first thing that we're going to ask to do is 128. Now, I am representing this as a solitary node. I have a label on the node, and then I have a circle denoting this is a node in a graph. This is a satisfying heap of size 1, because 128 is the root, and the root is the maximum. I'm going to create a maximum heap, so I'm always going to have the maximum value at the root position. What am I going to do next? Well, I like my cat to do a lot of things for me, so I'm going to say, Kitty, actually her name's Ursula, right? I also talked to Torsia. I'm going to say, Torsia, I have another responsibility for you. And my cat will take out her operating system and write 128, and then she'll write an arrow going to another node and put the circle, but she won't populate the node yet because I haven't told her what her other thing to do is, right? I think humans sometimes use to-do lists for this, but I noticed my cat always uses the heap data structure, right? So we have 128, and we know that we're going to need a tree of roughly this structure. It's going to have to be a root with one child, okay? And so what are we going to do? We're going to put a 64 in, right? Now, this is all I have to worry about, right? Because I still have a satisfying heap. The maximum value is at the root. A non-maximal value is at a leaf. And this leaf is sort of leftmost. It can't be any further left, right? I guess I could have put the arrow over here and denoted that there was nothing over here, right? But whatever. I have a row with one entry in it. The undergrads didn't think this was funny, but I did. So I don't know if you know that A-OK is named after Ada Lovelace, but it is. That's common fact. It's a real fact in the sense that it is either true or false. It is falsifiable. We're going to rinse and repeat. So after I tell my cat 64, I'm going to say, I have something else for you to do. And she'll say nothing because she doesn't even squeak that loudly yet. But she'll take her little marker and she'll populate the next entry in the layer, right? So I already have the leftmost leaf on this layer, so I'll now add a right leaf. And I note that I am working at this time with binary trees. So after this, I will have to go to another layer. Okay, so I'm going to put in 192. Okay. I put the 192 here. And as I put the 192 here, my cat will gasp in horror, and everyone in the class will say, uh-oh. Repeat after me, uh-oh. We love audience participation. Right? Yes, uh-oh, Spaghetti-O. This is a disaster. This is a huge disaster. This is an unmitigated calamity because 192 is the maximum and is not in the root position. There's only one thing that we can do to resolve this. We're going to perform an operation called heapify. And when I heapify, I swap the newly inserted element with its parent until it is not bigger than its parent. There's a story about this in the Bible called the prodigal son, so you can look it up. This is covered extensively in human literature in a variety of cultures, right? Okay. Not big Bible fans, that's okay. It's the divinely inspired word of God. Okay. Okay, so we're going to insert a 96 here. And I think we can already imagine what's going to happen. My cat's going to create a new leaf. She's going to create the leftmost leaf in a new layer now because she's filled her previous layer. And she's going to put a 96 in there. And then she's going to panic, right? Because she noticed that this 96 is bigger than that 64. And she knows that's not allowed. She knows she's supposed to be bigger than her children. That's weird. Especially early in life, right? Before they've had time to eat, right? She's only like 12, right? So like she should still be bigger than any children. Okay. I guess I actually don't know how long cats get larger. 3 years? Yes, I don't have a 12-year-old human daughter with children. Um, moving on. Perhaps not soon enough. What are we gonna do? Well, my beautiful baby cat daughter is going to notice that the 96 is not larger than the 64. Panic. Perform a heapify operation. She's going to switch the 64 and the 96, and then she's going to notice that the 96 is smaller than the 92, not continue to swap. She is going to notice that these are tastefully chosen, that 192 is twice as big as 96, which she appreciates because she knows the binary representation of all of these, right? Yeah. It's 64 plus 32, right? Do y'all see that? Okay. That's fine. Yeah. Now, I could have been doing all this with these beam pointers, right? And I did like a slightly contrived example where I very clearly only stored things that I could fit in 8 bits, but I did that to make this math look better for me. If I was storing this in a binary tree data structure, I would be storing data in 8 bits, and then I would have two 64-bit pointers for each value. And many of them would be null, mind you. This would have 2 null pointers, and this would have 2 null pointers coming off of it, and this would have 1, right? So we're wasting a ton of space. What this means is I'm storing 8 bits of information, and 8 plus 64 plus 64, 136 bits, which means I have a 64 or 16x overhead. That's like almost as bad as the overhead on 496T. Remember when I divided by 5 by 3 and found out it took 25 kilobytes? That, like, this could be us again. We could be that bad. But we don't have to be that bad. Instead, our heap can just be an array. Overhead of 0. Why is that? Every time I add something to the heap, I just put it at the end. Put it in the, I don't know, sort of like the last position, right? And so I just sort of start numbering my nodes, and I already know what the last one's going to be. So given the size of a heap, I know where everything's going to be, right? And I always put things in the same order. So let's construct the correspondence here. If I take the heap 192, 96, 128, 64, and that's not the order I added things, but that's the order the positions got added, right? I can just write that down as an array, 192, 96, 128, 64. I'm not losing any information. All I have to do is be able to cognitively keep track of the fact that 192 is the parent of 96 and 128, and 96 is the parent of 64. If I were to add another element, it would go right here, and it would be one of 96's children's. So 96's right child will be right here. If you don't believe me, that's okay. I'll show you. So my cat breaks out her whiteboard. Actually, she uses a whiteboard. She's kind of like a retro, so she uses chalk. And I say, hey, I've got something for you to do. I'm going to ask you to do 160. Just no problem. adds another box to the end of her array, which corresponds to adding this leaf to her heap. She populates it with a 160, and she gasps in horror, right? This is a disaster because 160 is bigger than 96. So she has to perform a swapping operation. She has to swap the thing she added fifth with the thing she added second. And she knows this because she knows the thing she added second is the parent of the thing she added fifth. So she performs the swap operation in the array or in the tree. It doesn't matter. They're logically identical. And then at the end, she has this as her array. Wait, is that actually wrong? Yeah, that is wrong. Should be there. You are all taking a class or probably you are all taking a class that is using one indexed arrays in the R project for statistical computation. And many high and mighty computer scientists like to bemoan and wail and complain and generally show themselves not to be appreciators of programming language theory when they're subjected to the sheer joy of using the R project for statistical computing. And one of the things they always complain about is like, what am I? Some sort of non-computer scientist using one indexed arrays. And those people have exposed themselves as never having implemented the heap abstract data type, which benefits greatly from one indexing. Let me show you how. 0 is the parent of 1 and 2. Not really a graceful way to do that. But you could argue maybe that like if you int divide the index plus 1 and then subtract 1 from it after you do that, you get 0. So 1 plus 1, I don't know. Right? Disgusting. We can one index, yeah.
I was realizing there is like a kind of binary relationship to the level.
Mhm.
Or is that kind of where we're going and keeping track of that?
It's exactly where we're going. You can determine where your parents and children are by dividing by 2 or multiplying by 2. And the only complication is one of your children is at double your index plus 1. But that is only true if you one index. Look at this example. 1, if we multiply 1 by 2, 2 is one of its children. We multiply it by 2 and add 1, 3 is one of its children. 2 has 2 children, we multiply 2 by 1 and we get 4. 64 is one of its children. 4 plus 1, 96 is one of its children. You can go back, you can figure out your parent. 5 is trying to figure out who its parent is, no problem. It integer divides itself by 2. Boom. 160. That's exactly where its parent is. Then it needs to know that node's parent. It divides itself by 2 and gets 1. So this sort of, by making the binary increase, every row is going to get twice as big, everyone's going to have twice as many children. That means we can always multiply or divide by 2 to go up or down. The next index is 6. Let's look at this example. I'm going to put a 224 there. Ooh, pretty big number. All right. What is that? That's 128 plus more than 64, plus some large amount, because that's 128 plus 64. It's 92 plus 32. Okay. So this is 128 plus 96. Sure. Yes, because 64 plus 32 is 96. Yeah, I see. It's OB1110000. It's 3 ones followed by 5 zeros. Yeah. It's just, we're going to do a bunch of integer division by 2 in just a minute, so get ready. But we're going to do it over numbers as large as 6, so we're safe. Yeah.
Do we have powers? Or does that, do you have to have another data store?
Use powers for what?
So, like, I was looking at the levels, and like, there's a pattern where, like, at the first level, it's to the power of 0, and then at the second level, it's the power of 2.
Yes.
For this, but I guess we would have to keep track of the levels throughout the work. And so are you using integer division because you don't have to do that?
I'm using integer division because I'm relating parent-child relationships, and the parent-child relationship, they're offset by the size of the level. And so they're offset by the size of a particular level, and the particular level can be determined by the index. So when we say that the levels increase exponentially, each level gets twice as large, which means the size of the jump to get to the next level is twice as large, which means I can take my index and double it, and that tells me the position in the next level. So it is the power. It's just we're only doing one step of the power at a time because we're going from one layer to the next layer. We're not going from the root to the final layer. But like if I wanted to know my great-grandparent, I would integer divide myself by 2 to the third. And that would just tell me. Okay, I'm putting 224 at index 6. I'm one indexed, as I want to be. I'm going to do an integer division. I'm using C-style integer division, so single slash. And the integer division of 6 divided by 2 is 3. So I'm going to consider this location. I note that 224 is larger than 128, so I am going to perform a swap. 224 is now in position 3, 128 is now in position 6, right? Now I'm going to recurse. Considering from the position of 3, holding the current value 224, I'm going to evaluate if I am still larger than my parent, right? This is usually what children do before they move out, right? I don't know. That was funny, right? Shout out children and also parents. I think those are the two things you can be. Actually, I should be shouting out legal guardians. I think that's more wholesome. Okay. So we take 3. We integer divide 3 by 2. There is 1, 2 in 3. Why is 1 afraid of 2? Because 2, 3, 4. Okay. That wasn't even funny. I don't even know what I'm doing here. Okay. And so 3 int div 2 is 1. So we compare it to 1. We notice, oh, gasp! Oh, my cat is shrieking in horror, right? 224 is larger than 192. This must be corrected immediately. Not to worry. We swap. Do we swap? Yes, we do. 192 and 224 swap, and then we are heapified. The maximum value is in the root position. And if we consider the subheaps, 160 is greater than 6496, and 192 is greater than 128. Easy peasy. This is what it looks like. I was secretly working with a tree the whole time. Could you tell? Did you feel the trees? Right. Okay. That's heaps. And I think we can all agree it was heaps of fun, right? I didn't hear a single person say that's not a heap of fun, right? With the benefit of heaps behind us, hopefully we now have some intuitive sense of how we can take a tree and just kind of shove it in an array and just like smooth it over and hope everything works. Right? How are we going to do that? Well, not to worry, I have a plan. I have selected 6 of my finest transactions. Some of you may be familiar with some of my work. For example, BC2. That is the year Caesar Augustus. I don't know what happened in 2 BC, right? CD3. That's my initials and also my third favorite number that is sorted integer monotonically increasing, right? We've got GC2. That's my second favorite group chat. That's where all of the friends I met in college are because they could never replace the friends I made in high school. So they're my day ones, right? I didn't make any friends in middle school. That's not true. I met my partner in middle school. Okay. But we were both in middle school at the time. So I don't, just for the record. It's like, yeah, I met my partner in a middle school math club. It's like, we were both in middle school. Okay. So whenever I talk about peaking in middle school, and also I talked to my partner about how I peak in middle school, she's like, no, and I was like, no, it's when I met you. Just like, I thought it was cute. Okay, in a complete binary tree, the last row is a power of 2 in size. Uh-oh, oh no, oh, what are we gonna do with that? Okay, this is not to where I have a plan, don't worry. We have 6 entries, so we're going to need a part of a row of size 8 and part of a row of size 4. We'll just start with the row of size 4 and add leaves until we get enough, right? No problem. Watch this. Okay, so I start with my my tree, and it's got 4 leaves. That's not enough. I have 6 transactions, right? You can't just make 2 transactions share a leaf, right? That's disrespectful, right? That's my third favorite integer if you sort the integers monotonically increasing beginning at 0, right? I should have said the natural numbers. Okay. So I need a few more places I can store hashes of transactions, right? Not to where I have a plan. I'm gonna take one of those leaves and I'm just gonna put 2 leaves on it, right? Oh, that's still not enough. That's only 5. See, I have 5 leaves. 1, 2, 3, 4, 5. But I did notice that when I gave one of my leaves to children, it increased the number of leaves I had by 1. And so I went from 4 to 5, and I just need to go from 5 to 6. So I'm just gonna pick my next leaf and start adding more rightmost leaves in the last layer. So I'm going to take the sort of third leaf there, this one, this thing. I'm going to give it some children. There, boom. 1, 2, 3, 4, 5, 6 leaves. Easy. Okay. Now I'm going to do something that everyone hated. And I think that this tree looks really nice and it's all at the same layer. I'm going to use my graphics package, which I'm not super good at using yet. And I'm going to place this graphic on top of this graphic. And when I do that, all of the rows are going to get jumbled up and everyone's going to complain. Okay, so just be ready for that. But it's still the same tree, I promise. And I can prove to you it's the same tree because this is all open source code and you can look at the code that rendered the tree, right? Okay, so I got my transactions, I got my leaves, and now I'm going to start relating them to each other. And I'm going to relate them to each other in this exact way, okay? So, oh, it does kind of look ugly, right? This is the root, left child, right child. The right child has 2 children. Right child has 2 children. Those are the leaves, okay. Left child has 2 children that each have 2 children. That's all that's going on here. These 2 we would perceive as being at the same layer. Okay, so I'm going to relate my transactions to my leaves. Each leaf has 1 transaction. Okay? I'm going to hash each transaction. I just adopted some shorthand here where transaction AB1, I just stylized that as HAB1, right? But I'm hashing the transaction. It's an SHA hash. Doesn't really matter. It's an SHA hash. The Merkle tree doesn't describe the hash that's used. It's just an idea. But Bitcoin uses an SHA Merkle hash. There's now something called fast Merkle trees because someone noticed they were computing a lot of SHA hashes, and that's the expensive thing to do. They don't look that interesting, so I'm not teaching them to you, but you can check them out if you want to. And that'd be a good extension for the final if you're bored. Yes.
The letters are, what did you call them? Keys, not senders and receivers. And the numbers are the
I was calling this the sender, receiver, and amount. Here, but it's a transaction. It doesn't matter what it is. And in fact, in the Merkle tree definition, is you can use this to store anything. So I just wrote something down to represent that. Okay. Now, this solves the problem of hashing a bunch of transactions, but it's not really a whole lot of treeing going on here, right? This thing sort of looks an awful lot like an array to me, and that's not very exciting. So what I actually need to do is I need to compute hashes in all of these, and I'm going to hash them. And this one does have the arrows going in the other direction, right? So I'm going to compute the hash here of these 2 values, okay? So it's hashes all the way up, and I've also given myself numbers so that I can refer to things that are hashed. So for example, the root here, this contains the hash of the value at position 2, which is this one. It's left child, and the hash of the value at position 3, which is this one here. It's right child. There is one typo here. Please don't get confused by this. I accidentally changed AB, which is supposed to be here, and 8, 9, which is supposed to be here. Just don't look at that. Look at these 3. So we hash the hashes, and this is hashes all the way up. This gets me to a Merkle root. This Merkle root if there is alterations to any one of these transactions, the Merkle root will be changed. So as long as you get this set of transactions and you hash it all the way up, you can be confident that it was not tampered with. Yes.
Where did base 64? Didn't you say something about that a long time ago?
Yeah, it's used for something.
Oh.
Bitcoin uses base 58, which is derived from base 64. And I think they use it to store public keys because the public keys are in binary. I just left everything in binary here. But especially in 2008, there was a lot more nervousness about pushing binary over wires because people wanted to look at it and verify its integrity. So the reason base 58 is used, and I just taught you base 64 because it's mathematically nicer. They took out the symbols that look the same. So all of the one I and L and the two zeros are removed. And the reason for that is so people could literally look at the transactions and see if they looked like they were tampered with. I think that's what I heard. I guess I don't know if I believe that's true. I don't know. Whatever. Okay. All right. 3 slides left. Or 4. I don't actually know. Is 72 minus 68 4? I think it is 4. But I. Oh, wait. Is your hand up? Hey, what's up? How long has your hand been up? Oh, thank goodness. I was like, am I losing my mind? Okay. Yeah, what's your question?
So you're not going to find, but
You'll immediately get an incorrect hash, right?
what if you can you
Yes. So the question is what prevents that? And so this verifies the integrity of transactions that have been accepted. So we take as given these are accepted. The way to determine if these are valid is you go look at previous blocks and you make sure the spender somewhere in that previous block is receiving more than they have spent. And the way you can verify that someone can't lie about that is you need to have that person's public key to sign one of these transactions. So there's 2 steps of verification. You verify that the sender has enough coins, and then you verify that it is the sender that's signed with their public key the appropriate transaction. So no one can impersonate me, and the blockchain authorities are going to make sure I'm not spending money I don't have. And once those steps have taken place, then we ensure the integrity of all the transactions, put them in the blockchain. So yes, it's a many-step process. The big Bitcoin mining nodes have to do a lot of math all the time because they're finding out if someone has the coins they're trying to spend. I believe, and I don't know, that so I mentioned a Bitcoin as a chain of ownership. I'm pretty sure that there's a separate data structure that you maintain on your mining node that's not part of the blockchain. It's just for convenience. And it's probably the key value pairs. So every Bitcoin is stored under the key of its current public key owner. And so when you see a transaction, you hash the public key in a hash table sense, not in an SHA-256 sense. You look them up in the hash table and you see their current net worth. And then you deduct their net worth from it, right? So that's how I would implement it. I don't know how it's actually implemented in Bitcoin Core. When they first started out, you didn't have to do any of that stuff because 6 people were using Bitcoin. Okay, so you just look. You're like, oh, Satoshi Nakamoto still has 21 million Bitcoins. It's like, yeah. I think that's a separate technical problem, but it's interesting that it's not part of Bitcoin. Like you've read the Bitcoin paper, and Satoshi Nakamoto just hand waves this. Is like someone will make sure you have those coins. It's like who? It's like, well, it just wasn't a big problem when no one had coins, right? So there's been some secondary solution, and I'm sure it's key value pairs. Yeah. They're trying to find the hash of the previous block that satisfies the proof of work. Because you have to have it be hard to find the hash in order for it to be non-trivial so people can't falsify it. And so mining happens after all of this stuff is built. You build the block, except for, I can't highlight it, it's very small, the number that is used once. And at some point, you know the next block is going to need the hash of the current block. And the hash of the next block has to start with some number of leading zeros. So you start trying different nonces. And you try different nonces until you get the appropriate number of leading zeros. When you get the appropriate number of leading zeros, that block is finalized and people start working on the next block. And so the mining step is you hash this block many, many times with different values in it. I've still bamboozled you, by the way. There's still bamboozlement on this slide. I'm sorry, I didn't mean to lead you astray, but you actually know in the exact manner which I led you astray. I've taught you everything. By the way, it was an array the whole time. Oh, there wasn't a tree. Oh, look, yeah, look, I put it in an array. See, look how beautiful my array is. Look how annoying the arrows relating the array are because of how the leaves work, right? But this doesn't actually matter, right? Because the transactions, it's a set of transactions. They're not ordered. It doesn't matter. You just put all the transactions in there. Here's another thing that's going on. Someone clever, I don't remember who, sorry, good job, whoever it was, noted that the arrows go in a different direction here. Yeah, there's absolutely no requirement that you put these hashes before the hashes of the transactions. You can just put these transactions in a Merkle tree and start hashing pairs afterwards and then working your way down to one. So it doesn't matter what order this array is in either. It just matters that you have all of the hashes somewhere. So we can serialize our Merkle tree. We can serialize our transactions. We put that in the hash of the Merkle tree root in our blockchain, and we can also serialize the blockchain. So the blockchain can be stored in a single file that you add one block to every 10 minutes. You probably hold on to the full Merkle trees for every transaction if you're a big mining node. And if you're just using Bitcoin, you probably don't hold on to it. And then probably if you're a big mining node, you also have a key value pair storing who owns all of the coins at any given time. And I think that's the totality of Bitcoin. Yeah.
How do you, on the array, get to checking the hash from your transaction lead?
How do I get from the tree to checking the hash of the transaction leaf? Why am I checking the hash of the transaction leaf?
I thought that was the whole thing.
Right. Okay. So I'm verifying some transaction. Right. Okay. So this Merkle tree is stored somewhere. And so when I get a request for a transaction, for example, from D, and D wants to spend 3 coins, the way I can verify they have those 3 coins to spend is a combination of things. I verify that it's their public key that has signed the request, so I know it's D. And then I verify that someone transferred D 3 coins, which I find by finding this transaction, finding the hash of this transaction, and verifying that hash is in the Merkle tree. And if I don't have this Merkle tree, which I might not, I recompute the entire Merkle tree from the transaction history, which I must have because I have to know who has coins. And then I verify the Merkle root. I either have to save the Merkle tree or rebuild it. And so I think big nodes that process transactions save all of the trees.
A better question, is there a way to verify the transaction without traversing the entire tree until you find the right?
I suspect I suspect it's not a like brute force traversal. I think there's a hash table somewhere that has pointers into this, but I don't think that's part of the blockchain because that's not it's not security critical how you do that, right? It's an efficiency benefit, So it's not defined by the protocol. My assumption is all of the transactions are stored under a key value pair storage, but I don't know. And I think like no one knows. I bet every Bitcoin miner does it differently. And that's probably an advantage Bitcoin miners try and have over each other, is having better key value store. These are the data structures as I would use them. Not too exciting. But it's just a bunch of sizes and pointers. They're all just Pascal arrays. You can store everything in a Pascal array. You just have to be willing to suffer, which we are. That's why we're here. Yeah, no, keep going. Heaps was just the motivation to explain that I could put this in an array.
But this array is not.
Nope. I tricked you a little bit because I kind of thought you should all know heaps. I just taught it to you while no one was looking.
Okay.
So I think like I've revealed my hand on this a little bit, but sort of the 5 data structures you have to be taught for it to count as a data structure are list, binary search tree, heap, hash table, and graph. And we hit the last 2 today. And it's again, it is not my fault that Bitcoin happened to use every data structure, right? And I cheated a bit earlier too. So in the SHA 256 lecture, the first 45 minutes of that lecture was about hash tables for no reason. It wasn't for no reason. I'm evil. All right, that's all I have for today. Are we going to DevOps next week? No. Okay, we'll be here, and I will teach you about threat models and specification logics and probably Bushi automata. I will see you then. I had a really nice time working on the heap T assignment. It was going to be a tree assignment. I started working on trees and was like, geez, this is awful. So that's why I changed it to heap. I thought heaps were a lot cooler to work with. I did not do anything to make this assignment easier at all. So this is a sort of similar to division. It is a difficulty inflated assignment. If you want to make it easier, which is totally reasonable, I wrote the entire API assuming you would have to fix the size of inputs when you made the heap, and that is really, really hard to work with. So just only sort uint64Ts. And if you make a uint64T heap, maybe you'll have a good time, maybe you won't. You won't learn as much about pointer arithmetic, but if you don't care about pointer arithmetic, then that's fine. Cool. I'm gonna go home. Nice to see you all. We'll be here next week. Good job. Come talk to me if you have any final questions.